Welcome everyone. Good morning, good afternoon, good evening. Part two of our workshop. We did one set of the workshop last night about modern R&D. This morning or this evening or wherever you are, we're gonna sort of talk about farm vibes. And just before we start, I just wanted to give a quick housekeeping slide of saying, hey, this workshop is going to be recorded. It will be available later on for on-demand viewing through a link that we'll share later on. And if you have any questions, we will take the questions on chat. There'll not be no live Q&A because just too many speakers and trying to manage the schedule. We'll do chat in offline on the chat there. And over to you, Ranveer.
Wonderful. Thank you, Riaz, and welcome everyone to the second day of the workshop. So yesterday we covered a little bit about food production, and today we are going to be talking more about the FarmVibes.AI release we recently did. I wanted to start by putting a lot of this in context as to what are we doing in Microsoft and Microsoft research around agriculture and food. So to start with, as many of you know, we need to grow more food to feed the world. This is a very important problem where the world needs more food, about 50% more food compared to today's levels. It's not just about growing more food. We need good, nutritious food, and we need to grow this food without harming the planet. So to achieve this end goal of growing more nutritious food to feed the planet, one of the most promising approaches is that of data-driven agri-food systems. And by that, what we mean is not just the farming side of it, but the entire supply chain. If every entity in the food supply chain could gather data, use that data with artificial intelligence to drive insights, it would drive efficiencies in the entire food supply chain, all the way from inputs to farming, to the retail shop, to the food producers. Every entity can be more efficient, can save money, can do much better than what they do right now. And it can help us take a significant step forward in sustainably nourishing the world. So towards that, at Microsoft, as you know, we have been working on different aspects of the food supply chain. And today, yesterday, what we covered was a lot on the food production side. That is, if you're looking to produce food, better food, then how do you do better phenotyping, better genotyping? How do you do better computational chemistry? Today's focus is going to be more on the farm side of it. So one of the other things I wanted to mention that it is not just about capturing data, but if you could share this data across the entire food supply chain, it could drive even new efficiencies and new business models. So in our group right now, we are working on three different aspects, three different big research projects. Today, what you'll hear about is the first one on FarmVibes, which is building on the previous work we did with FarmBeats. I'll talk a little bit more about that. The other things we're working on in the group, one is on the food supply chain. You heard a little bit about it yesterday on things like building a knowledge graph or including information in the DNA tags. So there are things we're working in that space. The third big project that we're working on is food production. That is, how do you accelerate the innovation of new food types? For example, doing AI across the phenotypes and the genotypes, or across the genotypes and the chemistry. How do you use that to accelerate the invention of new ingredients? Today's focus is going to be on the first one, on FarmVibes. As some of you know, we did announce we open sourced an AI toolkit called FarmVibes.AI, which is about mostly focused on sustainable agriculture. So when we think of sustainability, as a lot of you know, agriculture is one of the biggest emitters greenhouse gases. Not just it emits close to 20% of the greenhouse gases and a lot more of nitrous oxide. In addition to that, agriculture is also the most impacted by climate change. That is, as you know, farmers, they depend a lot on the weather, and because of climate change, there is a lot of variability in the weather, and farmers need to be better prepared with it. But agriculture could also be a solution to climate change. And towards that, with the FarmVibes project, what we are looking at is building a lot of the AI capabilities to empower growers, to empower every entity in the food supply chain to be better prepared with climate change, to reduce the amount of impact that they have on climate change, and also potentially use agriculture as a solution to climate change. So towards that, today you'll hear from several people from our group on different aspects of the FarmVibes system. Leo will first introduce the entire FarmVibes.AI, what exists, what is our vision with what we are doing, and then you'll have Bruno and Renato give you the tutorial on how to set it up. That we've open sourced the Git in GitHub, but then you can go there and you can set up this entire system. We'll show you how to train models and one such sample workflow, which is on weed detection. We'll also talk about some of the new capabilities. For example, one of the capabilities that we've announced is SpaceEye, the ability to see through clouds in satellite imagery, which if many of you are in farming or working in ag tech, that is one of the biggest pain points, is once you have satellite imagery, what's happening below the clouds. We'll talk about another workflow. Eduardo and Roberto will talk about sustainability practices, and then I'll be back just to summarize and conclude this entire session. So one of the takeaways from today's session for all of you, I would request is, one, we want you to get a hands-on experience of how to use some of these AI workflows. When we've gone out and talked to a lot of practitioners in the field, we realize that a lot of people are experts in agriculture, but they're not really experts in AI, not a lot of expertise in the cloud either. So today we want to help unblock a lot of that through today's sessions. We want you to, one, take away of how do you use AI as part of your workflow, and as a follow-up, we would want you to reach out to us with things we might be missing or any other pain points that you might have when starting to use AI as part of your workflows. So with that, I wanted to hand over to Leo for the first session of the day.
My name is Leonardo Nunes. I'm a principal research engineer here at Microsoft Research. And as Ranveer mentioned, I'll be talking about introducing FarmVibes.AI, the tool that I've just open sourced, and that's publicly available. So for today's talk, I'll start with a little bit of motivation around the tool, what made us build it, and the thinking around why we believe it's going to be useful for building data-driven agriculture. I'll talk a brief overview over our workflows, the architecture of the solution, the different components we've built and why, and then their technical details to understand why we believe this is something that can really increase productivity for people building data models for sustainable agriculture, and then talk a little bit about the next steps and contextualize some of the other presentations that are going to happen. So data-driven agriculture, especially precision regenerative agriculture, has been shown to improve yield through better selection of seeds and cultivars based on soil measurements, for example, reduce cost by targeted application of herbicides, by combining multispectral imagery, for example, with drones and GPS-aware sprayers, and ensure sustainability by better stewardship of the land with knowledge of carbon capture by the soil, for example. Right, but it comes with several challenges. In particular, there's no single data source that is able to tackle data-driven agriculture in isolation. We need to combine different data modalities in order to really build solutions that are targeted for this. So, for example, if we consider satellites, they have very good spatial coverage, usually global, but with lower resolution, around part of meters, and a revisit rate that is on the order of days usually. On the other hand, if you look at drones, they have very high spatial resolution in the order of centimeters, but their revisit rate is very sparse, right? You're only going to fly that drone so often over your field to be able to gather data. And IoT sensors on the other hand enable the very timely measurements, but they have very coarse spatial resolution. Right? So dealing with all these data sources that are required to actually understand what's happening in the field and then build them is a challenge in terms of having these different data ingestion and pre-processing pipelines that needs to be harmonized and then combined to be able to, and then building these AI models as well that are able to then take these data and provide meaningful insights are all hard challenges that we are trying to tackle with the new FarmVibes.AI toolkit that we open sourced. So with that, the idea is to help by building low-code, no-code insights for agriculture on top of existing data providers, for example, FarmVibes. So the idea is that we already take care of learning how to ingest the data and provide ready-made workflows that takes care of how to take the data in and conform it to certain standards. We provide information on how to merge data from field to satellites to better help understand what's happening in the field. And then we provide models and training examples on how to combine these different data modalities into meaningful models. And we are trying to look at this from a data scientist, either in the academia or industry point of view, where they need to connect to different data sources, pre-process the data, train and build their insights, and then infer for different regions. So the idea here is that through the workflows we provide and the examples and models we are showcasing in the OSS, we are going to provide an easy way for building these new insights by combining existing workflows, generating new insights, and then providing this loop where you can then infer what's happening. For example, add new data modalities where you see there is a gap in the performance of what you're building, and then iterate over this, providing a kind of consolidated tool for data scientists for the data on the agri-food space. So, and core things that we have in FarmVibes.AI is workflows. And workflows are defined for us, as I mentioned, as a kind of low-code solution. They're YAML files. In essence, they define a sequence of steps necessary to provide some desired data, but they have a common way of being used, meaning the inputs are always going to be where in the world you want to run. So basically the polygon, the geopolygon specifying where you're going to run that workflow, and the date range of when you're going to run that workflow. And all workflows inputs follow these kind of steps. And from there, we are able to running different steps and tasks, provide the data that you need to get your insights. So just briefly going over the workflow, because in the other workshops talks, we are going to look more deeply into this. The workflow schema basically has a name. In this case, this is an example of the SpaceEye one. You have your sources, which provides the region and the dates. And then you have your sinks, which are your outputs. In this case, we're providing the SpaceEye rasters with the cloud-free imagery. And you define your tasks. The pre-process one, which is another workflow. So we have the ability here to compose workflows from other existing workflows, as well as ops, which are our kind of atomic compute units. In this case, we have one to compute the Sentinel shadows, so detecting shadows in satellite imagery, and another one that's the actual SpaceEye deep learning model that removes clouds. And then the edges are basically defining, in this case, this kind of feed-forward solution where one output goes to the next and to the next until you get your output images. Not in theory, you can have way more complicated designs where we have parallel paths as well as more embedded workflows within workflows. And how do you actually run them once you have FarmVibes installed in your system is through a REST API that's running locally. You can basically post workflow runs, and that will start executing the workflow in the background. And you can define where the workflow that you want to run, either by naming the workflow, as we have here, its name is, for example, SpaceEye example, or you can also put the whole workflow definition in the input. So this allows, for example, a data scientist to create new workflows and then submit them through the API. And we also have, I think, a more user-friendly way of interacting with all of these, which is our Python client, where we can just open up a Python notebook in Jupyter, for example, and interact with the system by posting the workflows, querying to see if they are completed. And we'll have a lot of several talks showcasing how to use the client. And for the backend, what's happening is we have what we're providing as the client is running in your computer. That's the code that's available in GitHub. And as you go through the installation processes, what we're bringing in is a series of Docker container images that are then orchestrated and run in your local machine, basically setting up a local cluster for compute. And what are the major components there? We have the REST API, as I mentioned, which is what is interacting with the client, receiving those post requests and any other requests that's supported. You have the orchestrator, which is responsible for splitting, taking in that workflow definition file and figuring out which tasks need to be run and when and what are their dependencies. We have a cache service that avoids recomputing avoids recompute of the operations, and I'll go into a little bit more detail on this next. And you have several workers which are actually doing the compute. And as they are doing the compute, they are talking to a storage layer, which basically stores all the intermediate outputs as well as the final outputs in the local disk. So going into a little bit more detail in the workflow orchestration, it's responsible for first workflow parallelism. So as you run workflows, if you're running two different workflows, they're going to be run at the same time. We also take care, for example, if you have two different pathways in the same workflow that can be run simultaneously, they are. And that also has, and so this kind of is done for you by the platform, right? And we also have another great mechanism for reducing compute time, which is an automatic fan out and fanning mechanisms for the workflows. So imagine you have one workflow where you list a series of rasters that needs to be downloaded. We automatically fan out those requests to several workers, then download the data in parallel, and then fan in the results, providing a list of the downloaded rasters. And this is done automatically without any need of intervention from the user, right? So this is just by the actual orchestrator figuring out from the workflow definition what's able to optimize. And the orchestrator also provides resiliency and robustness to the workflow. So if you download a broken file during one operator, it automatically rerun some of the ops. It also provides a kind of observability over the whole workflow, so we know exactly which steps are running and which steps and how long which steps needs to be run. For the cache, as I mentioned, in that cycle for the data scientists, we expect, as we're creating the data sets for training and building models, as you're gathering information for kind of exploratory data analysis, you're going to be running things over the same region multiple times or over the same region over multiple years, right? And what we wanted with the cache system is to provide an easy manner of someone interacting with that system without having to worry about, oh, which data should I store? Where should I worry about saving that part of the workflow versus the other? So the cache solves this by storing the output of each operation. So we store the output of the atomic unit of compute we have right after each execution. That means that if you repeat the workflow execution multiple times, it has no cost. We're just even if you're posting a new run, we're just retrieving the output from what? From the cache. And it has the advantage of, because you're doing this at the up level, even if you have two workflows that share most of the compute, if you run one and then you run the other one, we are going to use the previous workflow execution to leverage the results for the new workflow. So you are never going to run the same op twice, basically, with the same inputs. And this also works at the granular level because of our fan out and fan in mechanism, where if you run a workflow from January to October, for example, and now wants to run from you want now to increase the results to include November, you don't need to run just a workflow from November, from October to November. You can just run the same workflow now going from January and increase the date range to November, and we are only going to do the incremental compute necessary to provide the output for that extra month. So the same happens if you just increase, for example, if we increase the polygon to include more spatial data, we're only going to compute the incremental compute necessary for that extra geometry we added, and not recompute for the whole region whenever possible. And in the storage layer, what we are actually providing is a local storage in your host computer at the moment. So all the data is stored locally, no data from the stored outside. Each output is actually a spatial temporal asset catalog, which is a common schema and a widely used by the community for geospatial data. So in case you want to interact directly with the outputs without going through the platform, that's also possible. And it is in a standard format. And also, you don't need to even worry about paths, because once you're using the REST API, every time we're providing a path to a local asset, to your results, they're all referred back to your local environment. And which workflows do we have available? So we have quite a few, from data ingestion, data processing, a category where we're calling FarmAI. These are kind of more complete workflows that leverage the data ingestion, data processing workflows to provide higher level insights into for farmers. And we have a few machine learning, more standard workflows. So for data ingestion, we support several satellite constellations from Sentinel, Landsat, and Airbus. We have good data sources for if you want to train or gather information for model training. For example, Cropland Data Layer is available. So that is a product from US government, where you have the basically for each year where each crop was grown, right? And then you also have nape imagery, which is another publicly available data set that's a yearly higher resolution, 1 meter per pixel data for visualization. And we have other data sets such as soil grids for soil information and elevation data. We also provide a suite of weather-related data sets, such as both for forecasts as well as historical data. We have, as I've mentioned, and we'll detail more in one of the workshop sessions, we have the SpaceEye, which provides daily cloud-free satellite imagery based on top of Sentinel-1 and 2. And we also have the ability of ingesting data that you have as a user so that it can be combined with the existing workflows we have. So this basically, you can either add a REST direct at the moment for it, or you can have your own input as a geometry. For data processing, what we have basic processings over rasters, for example, such as flipping the raster to a given geometry, computing the gradients for rasters. There are several indices such as NDVI and WI, computing linear trends, over multiple rasters and reprojecting rasters, as well as thresholding and providing time series statistics once you have a raster. And we actually use all of these workflows into the workflows I've mentioned in FarmAI to provide a canopy cover estimate for a given field, detect anomalies or changes in time series for a farming field, detecting emergence when an emergence happened on a field, as well as detecting methane emissions, providing NDVI summaries, as we're going to detail in one workflow as well, the weed detection one. Soil carbon what-if scenarios, where we do forward-looking projections of how much carbon will be stored in the soil, given a set of farming practices. A series of conservation practices workflows that tries to estimate things such as terrace farming, and a land degradation workflow that tries to estimate how much land is being preserved over time in a given region. In the ML1, we have the cropland segmentation model, which is a model that we'll be showcasing in another session, where we try to estimate where we have different, basically where crops are being grown in a field. We have a data set example where it's a full-on workflow that generates a training set that then can be used for training deep learning models. And we have one new workflow now for detecting driveways, which the next was done in collaboration with Terrain AI, that tries to detect driveways in urban areas that are suitable for electric vehicle charging stations. So what are we discussing next, right, in this workshop? We have two tutorials, one on how to install and on the REST API, and specifically on the Python client, how to use it. So the idea here is getting you from zero to running your first workflow. Then we have the model training inference in FarmVibes. So how can you actually use FarmVibes to train a new model? And then we're going to do the deep dive in a few workflows, showcasing how we actually build these higher level workflows on top of existing ones. So we have SpaceEye workflow for the cloud-free daily cloud-free imagery. Weed detection, which is a really interesting showcase, as we shows how we can, from a drone imagery of a farm, detect weeds and then provide actual polygons of where weed is present, that then can be used, for example, by a smart sprayer to only spray herbicides on those patches, right? So there's a workflow where you can actually go from flying a drone to then doing smart spraying and closing the loop from data acquisition to actually doing something actionable in the field. And then they choose sustainable practice workflows for terrace detection and land degradation estimation. And what is next for FarmVibes.AI, right? We continue to work on several new workflows that will be pushing to the GitHub repo soon, both on better water, a lot of them on water management, on more sustainable practices, for example, as well as different carbon measurements. And the plan is to add new deployment options as well. I've been talking a lot on how you can run these on your single machine, your Azure VM. We plan to add a lot of options in terms of you being able to really scale these out if you want to run on larger areas or build bigger models. And we plan to provide more training examples on how to really build powerful AI models on this multimodal data. All right, so I think that was it for my introduction to FarmVibes.AI. Thanks a lot, folks, and stay in touch. And please go visit the OSS and provide any feedback. Now with Bruno and Renato, who will do the introduction to the how to install and run FarmVibes.AI.
Hi, everyone. Hope you can hear me okay. This is Bruno, and today we're going to talk about how to install, how to configure FarmVibes.AI, and how to use the Python client and execute some workflows, even taking a brief look on the REST API that's provided, right? So I'm going to talk about a little bit on how to install it and configure the cluster out of nothing from scratch. And Renato, we're going to talk about the workflows, the Python client, and the REST API. So let's begin. What are the requirements to execute and run, install FarmVibes.AI? So in terms of hardware, we need a Linux machine with Ubuntu 20.04 or more recent version. At minimum, 16 gigabytes of memory, 32 gigabytes is recommended, at least 4 CPU cores, and 512 gigabytes of storage. In terms of software, we need Git, we need Docker, we need curl and Python. Git to download the repository, we need Docker to manage the containers that will be running the workflows. We need curl to download additional software required by FarmVibes.AI, and we need Python to execute the Python client. So this is the web page of our project. As you may know, it's available on GitHub. So if you access github.com, Microsoft FarmVibes-AI, you should be able to see the download the code, execute, and check the documentation. So my presentation will be divided into different, let's say, machines. So initially, we're going to create a FarmVibes VM, right, using a bicep template. And to do that, we're going to use a host machine, a host Linux machine. So the first part will be, I will execute or show how to execute commands on your host machine to create the FarmVibes VM, right, using bicep template. And the second part, I'm going to show you how to use that created VM to configure the cluster. So how to deploy in Azure FarmVibes.AI VM. So let's see how it's done. But before presenting how to do that, let me briefly introduce you what's an Azure Bicep. So Azure Bicep is a declarative domain-specific language to deploy Azure resource, right? It supports all the resource that's available on Azure. So it can be computing, network, storage, all the resources that are available there, you can deploy and manage using Bicep templates, right? It has a simple syntax when compared to ARM JSON templates. So actually, the Bicep template is translated to an ARM template and then use the Azure Resource Manager to deploy the resource on Azure. So it has a repeatable result. So as long as you have the same input, the output will be the same. So it allows us to perform some previews on changes that are about to be made. So you can perform some what-if analysis before deploying the actual resource. So let's focus on the creation of the FarmVibes VM. Initially, we need some requirements to create this VM. So you need a Linux computer, or some WSL on Windows. So just like this one, right? This prompt. So you need a command line CLI to execute the commands that are about to be made. And you need Azure CLI installed and some Azure subscription. You can just go to the Azure website and create a subscription if you don't have a subscription for you, and the resource group in which you are a contributor. Also, you need a SSH public key, right? If you don't have a public key available for you, you can just create a new one using SSH keygen command and use the default parameters, and then you should have a public SSH key for you. Okay, and what we're going to do is to show you how to actually create the VM for you, right? The first step involves cloning the repository. So just we can perform a git clone on this particular address, right? So just clone the repository, and then the repository will be available for you. And also, you need to log into your Azure account that you just created or that you have. So AZ login should do the trick. It should present a token for you, and you can just copy this token and follow this link to connect it on your Azure account. And after doing that, after logging into the Azure, you can select your subscription, right? Subscription that you have access, and create the deployment. So the deployment is actually the creation of the VM. So let me zoom this command out, right? This command is available on the documentation, right? So basically, you perform some AZ deployment group create, right? Uh, and select your resource group. So on this red part, you can choose the resource group that you have access, right? Select the name of this deployment. So the name will be used in the next slide to check this SSH command to access the VM. You have to choose the template file, right? The template file should be exactly this path, and you should be sure you should make sure that you are inside the FarmVibes AI folder to perform this command, right? And provide the parameters. So we have 3 required parameters to create this VM. You need to pass the SSH public key, right? If you perform this last line command, so this should be the path of your SSH public key. You should provide the suffix name for your VM, so the name of your preference, and the encoded script. The encoded script will install the software required to configure and install FarmVibes. So after doing that, it takes about a few minutes, right? 3 or 4 minutes, and then you should see a JSON that will be prompted for you, the JSON file or output, right? If you scroll up the output, you will see the SSH command, right? But if you want, you can also perform this command AZ deployment group show, passing the resource group name and the name of the deployment to query the SSH command. So if you copy this SSH command, you can connect it to your new VM. The advantage of using this VM is that the VM has all the requirements that are needed to install and manage FarmVibes directly for you. So you don't need to worry about the configuration of the VM and the software related to install it. You also can provide some parameters on these additional parameters on this VM creation. For instance, suppose that you don't want to, or you want to choose the location of this VM or the VM size. You can look at the bicep template parameters and select one of them, right? And choose the parameters that you want. So just take a look on this bicep file that's available on repo, on the repository GitHub, and check what you can change. So once you have the VM up and running, how can we actually install the FarmVibe cluster, right? So basically, the next steps will be executed on the top of the VM, right? So basically, you need to clone the repository again because we have a brand new VM for you. And once you clone the repo, you can enter the repository folder, right? And if you don't want to create the VM, you can use your own setup or your own machine, right? And execute this bash command on the repository root folder. So if you execute this command, setup FarmVibes.AI VM, you will install the requirements in terms of software to execute FarmVibes, execute and manage FarmVibes. So to execute this command properly, you need to make sure that you have sudo permission on your computer, right? And an Ubuntu installation with the hardware requirements that FarmVibes need to execute, right? So just to check the requirements, the software that's required to execute FarmVibes, this slide shows how you can do that. So if you are able to run Docker PS or any other Docker command without sudo, you are good to go, good to install and manage FarmVibes. If you can execute some code, you can download the software required by FarmVibes, so you are good to go. If you can execute Python and Git, so we can set up the FarmVibes cluster. Regarding the management scripts, we provide this script that actually manages the FarmVibes cluster for you. So using this script, you can set up a new cluster. You can start the cluster that was stopped. You can check the status. You can destroy, update the image, right, for your cluster. And you can also add some secrets for your cluster. Suppose that you have a password that you don't want uh, to use directly on your source code, for instance. You can add a secret that will be stored inside of the FarmVibes, and the workflows can access the secret directly, right? So Renato will talk about some workflow parameters, and you can use some secrets as parameters as well, right? So let's do the FarmVibe cluster installation. To do that, you just need to use the management script. So if you execute the command bash FarmVibes.AI.sh setup, you will be able to install all the requirement software and perform the cluster configuration. So you will automatically install Dapper, Minikube, Cube Control, and all the required software uh, with minimal intervention. It runs automatically, right, and takes a few minutes. And if you see this message, FarmVibes REST API is running at a given address, the cluster is installed for you. So the next step of my presentation, we're going to execute a hello world workflow just to make sure that the cluster is installed properly, right? You can also perform some status checking. So using the management script, you can check the status of the cluster, and you will see the profile of the Minikube cluster and the IP, the port, and the status that in this case it's running, right? On the last step, we're going to install the package, the Python package to properly execute the Python client, right? Just to make sure that we are able to execute new workflows. For instance, here we are using pip install and passing the VibeCore package, right? So we're going to install it. And on the last step, we're going to execute the FarmVibes Hello World workflow using this script to make your life easier, let's say. So this script actually creates a new FarmVibes AI client, right? It lists all the available workflows for you. So we have a pretty big list of workflows that are available, and this list is increasing. And finally, it runs the Hello World workflow and check the results. If you can see the results of the workflows and check if the status is done, so the cluster is working properly, and you can proceed on the workflow and FarmVibes usage, right? So this concludes my parts of presentation. And I believe Renato is going to talk about how to install, how to use the Python client, the REST API, and workflows. Thanks for your attention.
All right. So I'm assuming you can see my screen fine. At least the feedback I have here is that that's the case. So, hello, I'm Renato, and I'm now going to talk about the Python client specifically, the REST API, and what are workflows and how they interact with the FarmVibes infrastructure, how you can write your own, how you can submit new ones, and query information. So, continuing from where Bruno left us. So we were just running these commands, so which essentially is going to run a module in the Vibe core package, and it just so happens to be called FarmVibes.AI Hello World. We are going to see during this presentation what these actually entails, but before any of that, let's see what these generates in the cache, in the storage. So when we run this, this module already has a geometry that just so happens to be in the United States, and so it's going to generate something like this. Maybe the zoom is not good, but you should be seeing a pixel, a red pixel in a part of the United States. If you can see it, well, it's around this region. Well, that's the input geometry we pass to FarmVibes, and the Hello World workflow is the one that prints Hello World, shows a map of the world, highlights your geometry in red, and any countries that intersect with it in orange. So if this works and this file exists in your file system, this means FarmVibes is actually FarmVibes.AI is running smoothly. So this module, it's available in our GitHub repo. Here it is, and it is a sibling of the client module. The client module is now what we are going to talk about. And well, the most important thing about the Python client is that it's actually a wrapper around the FarmVibes.AI or the TerraVibes, which is how we call the execution engine REST API. So the REST API, as you can see, it has a few number of endpoints. So one root that just prints out some status, a list of workflows. So what Bruno had shown us as a list of workflows is actually the output of calling this endpoint /workflows. And then a set of endpoints for managing workflows or workflow runs, which are the computation that we do on top of the workflows that reside on disk. I will be showing a couple of examples here interacting with the OpenAPI specification interface that we export. So if you executed the script Bruno just showed us, which creates a local FarmVibes cluster, then you're going to see probably a Docker network with a node that resides in this address, unless you changed the Docker default networking parameters. And it's going to export port 30,000 in that host. So you should be able to access the REST API using this URL. You don't have to make any notes, because when the script finishes executing, it will actually show you this address or whatever is used in your local environment. And anytime you need to fetch this because you don't know, or you forgot it, or something changed, calling the FarmVibes management script with the status argument is actually going to show you where it lives. So let's go through a couple of examples with the REST API, because then if you don't like our Python client, then you can write your own. So let's go. First of all, we are going to query the runs that currently exist in the cluster. So here, when we expand the get/runs, so these endpoint here, when we expand it over here, we are going to see a set of fields that we can tweak. And so here I want to get the name of a workflow run, which means the name that I, as a user, typed to identify that later, and the workflow itself. And this is a string that represents the workflow in FarmVibes itself. So when I just type these two fields, and we can query any field that exists in a workflow. You're going to see a few more in a few minutes. The UI is going to generate a curl comment that could be used, for example, in the command line, and the URL that represents the parameters that you just set. And in this example, we are going to see, well, I did execute a lot of workflows, so I'm just showing two here, just as an example. The first one is the hello world workflow, and this one is set by this script we saw before. And the second one is an execution of SpaceEye. Yeah, and more would follow, always having these two fields here. And going now to the posting of workflows. So these are showing what had already executed, but how do we request FarmVibes to run something? Well, like this. So the API is mostly self-documenting, and so we have, for example, examples in the UI. And when you expand the post details, you're going to see, oh, what a coincidence! It's just the definition of the Hello World workflow itself. So if we click and try it out and submit this thing, it's going to execute the Hello World that we just saw. And so here we can see a few more parameters which we will revisit in a few slides. So the name, so this is the name that we use for identifying, as I shown in the previous slide. The workflow itself, a set of parameters, but Hello World doesn't have any. And then the input itself, so a time range and a GeoJSON with the polygon that I've shown as well. So to the client, onto the client. Well, the client is a wrapper on top of the REST API, as I've mentioned. So we support not only the submission, but also cancellation, describing workflows, and the monitoring. So if you need to wait for a workflow or to run, you can use a couple of functions that we have there. And so you can write a synchronous script, for example. Not only that, but we list the existing workflows, and we can submit custom workflows definitions as well. So I've been talking about workflows for a while now, but what are they? Well, they are mapping. So we saw the name already, but they are mapping or Python dictionary or an YAML file. And they have sources, sinks, edges, tasks, which are nodes, and they can be of types ops or of types workflows. And because we believe that having documentation apart from the workflow itself would only have them out of sync, we actually keep the description and documentation of workflows close together. So with these terminology here, for the ones that know graphs, they probably have noticed already that we are essentially describing a computational graph. And so when we submit, for example, the data is actually fed into the sources of the computational graph, of the FarmVibes computational graph. And then the data is passed over the edges to each task, which are the ones that actually do the computation. Once everything is done, all computation is done, FarmVibes will collect the output from sinks. And as I mentioned before, with parameters and set documentation. Examples will follow, trust me. But then let's see the anatomy of a workflow step by step. So by now, what we have here is an example workflow, and we have all the required keys for this workflow. So let's see what the sources they would be. So if I define, for example, two sources, they now have names and they will appear in our representation. And by the way, this example is in the repo as well, in the GitHub repo. So we can take a look with more details there. And so we have these two inputs, first input and the second input. They are named. And when you submit something for FarmVibes to execute, you should then populate values for these inputs. And then they will be mapped to some tasks. And so here we have the inputs mapping to a first task, a second task, and a third task. And so we can see them on the right. So the first task, the second task, and the third task. Now, the second task is represented differently because we support workflow composition. And when we reference a workflow in another workflow, we have to represent it with something different. So we are using a circle for that. And whereas the other polygon is actually an op. And so we have the sources connected to some tasks. Now, the data from these tasks, it will flow via edges. And so we have these definitions of edges, of which we only have one. So we have this edge that goes from the second task to the third task. And the other edges that we are seeing are just for connecting inputs or sources. Then we have the sinks, and the sinks are the outputs. So here we have two outputs, the first output and the second output. And it is this example is complete because it just so happens that we don't have any parameters for this sample workflow. So now that we have an overall view of a workflow, let's see, for example, how the Python client can show the documentation of a workflow. So here in the Vibe Core package, in the client module, we have this very useful function, which is called get default Vibe client. And it will try to find your REST API, the REST API of your cluster for you. So once you call this function, if you have a cluster running and it was created with our installation script, that's it. You will be able to connect to the REST API. You don't have to pass any other parameters. Otherwise, you will have to instantiate a Vibe client and point it to wherever your REST API is running. And so here I want to see the documentation for the Hello World workflow. Well, it just so happens that the substring hello appears in the Hello World workflow definition. And so I'm able to list all the workflows, filter by the hello string, and then that will give me a list which has just one element for this case. And I'm able to see the documentation because now I have a reference to the workflow in memory. And I wanted to show this example because here we are able to see that not only we have the sources of the Hello World workflow, which are just a single one, the user input here, but it has a type associated with it. And so we have the data Vibe type in our client. And this is the most basic type that users interact with, and it contains an input geometry and a time range. We also have a output, and then we have the base raster output type here. And we know, and FarmVibes knows, that whatever comes out of these workflow execution is going to be a 5-core raster type with the highlighted countries I've mentioned before. And we only just have a single task, which is an op. And the cool part of having the documentation close together with the workflow definitions themselves is that if you go, for example, to the workflow list in the GitHub repo, you're going to see the list of all workflows that we have, and all of them will have a short description. Well, this short description comes precisely from the short description of these documentation we have here. So, for example, we have this part here, which is the short description for the Hello World workflow, and these would appear below in this list. Anyway, so that's a cool thing about these documentation part. Now we are going to go through examples of things that connect to workflows or that are part of workflows. And the first one is the sources. So this is an input for the Hello World workflow here on the right of the slide. And as I've mentioned, this represents a data vibe type. So this has a start date, an end date, and a GeoJSON with a geometry. And here I just defined a unit square, or it should be a unit square. And so this thing that we pass to the workflow, it's going to be fed into all the sources that we specify. And once the sources are connected, then tasks start execution. Now tasks are connected to other tasks. And so here we have a small part of a sub-workflow for the SpaceEye workflow, in which we are working with Sentinel-2 imagery. And all of these tasks that we define, we have 3 tasks here. So stack Sentinel bands, group Sentinel bands, and merging the Sentinel orbits. Sorry, so bands, orbits. And these ops, they are the most basic computational unit in FarmVibes. Right now, they are defined by us, but in the future, we want to add support for defining custom ops. But for the time being, users of FarmVibes, they are able to interact only with workflows. So we can define workflows and reference existing workflows. So all the workflows that Bruno has shown us today, they can be composed arbitrarily as long as the types match to create new workflows, which opens up lots of possibilities. Yeah, so continuing. So if before we had the tasks, now we have the edges and they are typed. So for example, in stack Sentinel-2 bands, we have an output port that goes from stack Sentinel-2 bands, and it has some rasters, and it goes into the input port of rasters of the next operation. Now, if for some reason, instead of doing this connection here, I had done something like this, so trying to map Sentinel-2 raster to the group Sentinel-2 orbits masks, then FarmVibes, if the types were different, it would trigger a typing error. And so if you have, for example, a categorical raster for a mask and just a base raster, you won't be able to match, to connect the more general type to the more specific one. So we can verify the correctness of workflows. when users submit them. All right, so workflows, they keep executing, they run, and finally we have to consume the output of the workflow, and we will have then the sinks. And so here we have two sinks, output raster and output mask. But this workflow is actually a bit complicated, so let's do an analysis of sinks considering the Hello World workflow. Well, in the Hello World workflow, so sinks define the outputs, as I've mentioned, and they are made available both in the REST API and the storage. So if I do a request, a GET request to /runs/ the ID of the Hello World workflow that I had submitted, I would see something similar to this JSON object on the right of this slide. And the most relevant part for us here right now is that we have a raster, and our raster has a set of assets. And of all the assets that we have, it just so happens to be one, we have an href with the path to the file that this workflow generated. And by the way, even though the FarmVibes cluster is running in a virtualized environment in your machine, our code knows what is the path according to the host machine, which is executing FarmVibes, which started the cluster and hosts the cluster. So this path is the real path. So you can just open up a file explorer and go to this path and see what is the output image, as we shall see in a few more slides. I'm making lots of promises today. But before we do that, I just want to cover one thing. As Bruno mentioned, so if you need an API key or a secret in a workflow, and we didn't have a way to parameterize workflows, we would be forced to hard code the secrets and API keys in the ops themselves or in the workflows themselves, and that wouldn't be nice. So what we do is we support parameters both to customize the behavior of runs. So we could select different algorithms for a given op if we had parameters for that. And the other possibility is for specifying API keys, which is the case for this example here. So I just sorted the NDVI summary workflow representation to show both that it supports the PC key parameter and its documentation. So if we want to download data from the planetary computer from Microsoft, we actually need a planetary computer API key. So this workflow needs this parameter, but how do we actually add this key to the cluster and to the workflow? Well, as Bruno has mentioned to us, in the FarmVibes.AI.sh management script, we have this add secret command, which adds a key with a given value. So for this specific case, we would run add secret, and in key here, we will use the PC key and whatever is our planetary computer API key for execution. And then magically, the NDVI summary would be able to use this key. And well, that's because the op that defines, that actually communicates with planetary computer, it has a reference to the secret, but it's still the parameter PC key. Well, that's a lot. So maybe we are now able to understand completely a single workflow, such as the Hello World workflow. So Hello World is the simplest one. It has a name. It just has a single input, user input, which maps to the user input port in the hello task. And hello task is the only one we have, which runs the hello world up. And we have a description, which is the same one that we saw in the Python interpreter. And finally, with all that, we can see what is the output of the hello world script, but now with code that we can write and understand. So here's a full notebook that can get the output of the hello world workflow. So here's our friend get default vibe client. We are getting a client, and then we can find the hello world run, and this is the first run, as I think I've mentioned before. And with here we can, so with matplotlib's image library, we can read an image. And so from the output of the hello workflow, which is the one from this cell here, we can go to the raster output. So this raster here is the same raster here. So we have we don't have to keep track of that, but FarmVibes will use whichever names we define in the sinks. So they are the names of the outputs. And we have a list of assets. We pick the first one, we get a path or a URL, and then we can load that and show the same image. Nice. So this means that this thing exists on disk, and as Leonardo mentioned, all op outputs, they are cached. So for example, in this first image, we see a snapshot of my local cluster. And I did execute a bunch of different ops, and in one of them is the hello world op. And when we expand this hello world op, we see that we have a stack catalog with a stack item and a stack collection containing the description of the hello world output that we saw. And for each of these ops, of these different ops, we will have their outputs. And here an example of the cache. So assume that we want to get some precipitation data from the chirps data set. And we do two runs. One of them downloads data from the whole 2019 year. And the second one has an overlap of 6 months between from the end of 2019, and then it downloads the data for the first half of 2020. Ideally, what we would like to see is that if we download in X time this first part, this second part should download in X/2 time, because we already have this first part cached. And so this is obviously not a scientific experiment, but we would like to see something like this. And when we run it, by the way, this is the output of the monitor in the client. So if you get a workflow and call .monitor, you're going to see this nice table. And we can see the download chirps operation, which is the one that actually does the downloading. We see that for the first run, we ran for almost 5 minutes. So ideally, we would like to see the second run for almost 2.5 minutes. And well, that turns out to be true with some tolerance, which is nice, I would say. So this is one of the advantages of the cache. And we not only do caching over time, but we also do a caching over regions. So the cache becomes quite powerful in running new workflow runs. And finally, I just wanted to mention the submission of custom workflows. So we saw the hello world workflow in which we had a hello task. So now I'm creating a new one, which has a hi task. And so we can define the hi task, the opt it runs, it's the same. And then the user input, I think that string is just too long, so I just want to use in. And the output as well, I don't want to reference a raster, I want to reference the whole world. So I made these changes. I defined these as a YAML file. I saved it as custom hello. So this thing goes into this file. And so now I'm able to load it, get our client, define some date range, get a region close-ish to São Paulo in Brazil, do a submission, call the monitor, see this nice monitor that now uses the high task. And finally, I can see the output here. Just a sec, let me erase all the ink. Nice. So here, the output, which was first, it was raster. Now it is world. And what else? Yeah, and we can see the high up here and high mapping here for the representation of the workflow. And that's all I had to say. I hope you enjoyed. Keep in touch. So Bruno and I, we added our social networks here. You can find us on GitHub as well. And please visit the repo, the FarmVibes.AI repo as well. And I'm sure you're going to find something that you like there. Right now, we have a break, I assume. Yeah, and that's it.
Thanks, Renato. Yeah, we'll have a 5-minute break and then, we'll start again.
Hello, folks. I hope you all guys are seeing my screen. Let me know if that's not the case. My name is Rafael. Today in this tutorial, I will show how to train a machine learning model leveraging FarmVibes.AI capabilities. So one of the goals of FarmVibes.AI is to empower machine learning applications that target important and complex problems in agriculture, sustainability, and energy. We do that by offering multiple workflows that facilitate different steps throughout the ML pipeline. The first category of workflows are the ones that take care of data ingestion. These download and pre-process data from multiple sources, preparing it to be the starting point for most of the other workflows in the platform. This includes raw data sources such as Sentinel-1, Sentinel-2, Landsat, and crop data layer, but also internal AI-enhanced data sources such as SpaceEye cloud removal model. Besides those, we also offer data processing workflows that transform data into different data types. For example, computing vegetation index or aggregating statistics of rasters. Finally, we also offer machine learning workflows that provide several highly customizable operations related either to training or inference of models within the platform. In this tutorial, we will explore the crop land segmentation task, in which, given a satellite image of a region of interest, in this case, a Sentinel-2 imagery, we want to obtain a segmentation mask of crops in that region. We will approach this problem in the context of FarmVibes.AI platform, highlighting how much of the data ingestion, pre-processing, and management in general are simplified using workflows. Just to give an overview of what we will see today, we will receive as input a geographic region of interest and a time range, and employ FarmVibes to workflows to download and pre-process Sentinel imagery. From such data, we will compute vegetation indexes and train a segmentation model using PyTorch. Finally, we will show how to deploy this trained model back to FarmVibes AI platform to predict crop maps for unseen regions. So our initial step is to download the Sentinel data. In a scenario like this of remote sensing, clouds can be a huge issue, obscuring parts of the region of interest and hindering a possible potential crop segmentation. When collecting the data, we cannot always be certain of obtaining cloud-free imagery for our applications. In this sense, an important workflow that is available within FarmVibes.AI is a deep learning model that removes cloudy artifacts from both by combining both Sentinel-1 and Sentinel-2 data throughout a window of time. This powerful in-painting-like model generates daily cloud-free imagery, despite the usual 4 to 5 day cycle of Sentinel-2. For more information on the SpaceEye itself, please refer to the SpaceEye in FarmVibes.AI session with Roberto Estevan that will happen in a few minutes, as well as the original paper in archive. With the cloud-free image, we compute the normalized difference vegetation index, or NDVI. This is an index that compares the difference between the near infrared and the visible red bands. The intuition behind it is that vegetation strongly reflects light in the near infrared spectrum, while absorbing it in the visible red region. So we expect that areas with a high vegetation concentration to be highlighted, or in other words, to have a higher NDVI activation, in contrast to non-crop regions. This NDVI raster will compose the bulk of our input data for training. As ground truth for this model, we will employ maps from the USDA crop data layer, or CDL. These are yearly segmentation maps that are available for the continental US, with which crop type, so for example, wheat, corn, being assigned a specific crop index. In our scenario, we combine all crop type indices to create a binary crop versus non-crop segmentation map. We use this as the ground truth for training our model. To generate the dataset that will be used for training, we employ a specific FarmVibes.AI workflow. The workflow receives as input a geographic region that is defined by a geometry and a time range from which we intend to collect data. It runs a workflow that consists of 2 parallel flows. The topmost one, which starts with the SpaceEye workflows, it downloads data for the region and time of interest, and then run the cloud removal object. This is followed by an NDVI computation, yielding a series of daily NDVI rasters within the time range. On the other hand, the bottommost flow performs the download and preprocessing of the CDL maps, yielding a map for each year in this time range. Even though Renato walk us through the anatomy of a workflow, let's see another example of this more complex one. So we are going to take a look at this dataset generation workflow just to understand how the components are linked. As we saw in Renato's session, workflows are defined by a set of sources, sinks, parameters, tasks, and associated edges. As a source for this workflow, we have the user inputs, which encapsulate both the geometry and the time range of interest. As for sinks, we have both the NDVI rasters and the CDL maps as outputs of our workflow. We have 3 tasks that compose this workflow, and they are the SpaceEye, the NDVI, and the CDL tasks. When we consider how the sources and sinks are connected to each task, we see that the user inputs link to both the SpaceEye and the CDL tasks. While the sinks, they are connected to the outputs of the NDVI and the CDL tasks. We also have an edge between the SpaceEye and the NDVI parts, linking the cloud-free output of SpaceEye to the NDVI computation itself. Each task that we define is associated with a FarmVibes.AI operator or workflow. These workflows can be used to compose custom workflows for your own problems and tasks. Finally, we also define the parameters that are exposed in this workflow, and in this case specifically, we are going to use the planetary computer key during download of data. Unfortunately, USDA provides a single CDL map for each year. So this might be an issue, as we might not be certain of which moment throughout the year that map is representing. To account for the temporal variance of fields during the year, we download data for the whole time range. With this data, we generate cloud-free images with SpaceEye model and then compute the NDVIs. In our notebook, we will compute NDVIs with a 10-day interval throughout the year. So this will yield roughly 37 rasters for a single year. The model that we will train receives as inputs a set of NDVIs stacked in the channel dimension, and we will output a cropland segmentation map. In this session, we will show how the training can be done either locally, but also how can it how it can be integrated with Azure machine learning. As the architecture of our segmentation model, we will employ a feature pyramid network, or FPN, with a ResNet encoder implemented by PyTorch segmentation models repository. The main backbone of this model follows a UNet structure with feature map connections between layers that progressively decrease the resolution of the maps. It also comprises of a series of segmentation heads whose predictions are combined for the final cropland map. Even though we are training with PyTorch, this could be extended for other machine learning frameworks such as TensorFlow, for example. Once the model is optimized, we export it using a library called Onyx. Onyx is a cross-platform training and inference accelerator intended to facilitate deploying machine learning models. It supports most of the machine learning frameworks such as PyTorch, TensorFlow, scikit-learn, while also being compatible with different hardwares and OS. In our notebook, we will show how this trained model can be exported to an Onyx file, and then deploy it back to the FarmVibes.AI cluster. This would allow us, for example, to use our model to infer the cropland segmentation maps of unseen data. Just like the dataset generation, in this final step, we also provide an inference workflow. The benefit here of using workflows for inference is that FarmVibes.AI will take care of downloading, pre-processing, and even parallelizing the model inference for you. In this scenario, we follow a similar flow of to the dataset generation workflow that we just seen. So we will download Sentinel data, generate cloud-free image, and compute the NDVI. The main difference is the lack of the CDL inner workflow and the inclusion of an Onyx inference operator that predicts the cropland segmentation map for us. With an overview of the components of this tutorial, let's quickly see how the code of the notebook is organized. So I will show you 5 notebooks today, each one responsible for a common step within the machine learning development. We will start by seeing how to invoke FarmVibes.AI workflows for generating the data set and also visually explore the outputs. For training the model, we will follow a local training and briefly see how such training could be integrated with AML. Finally, I'll show you how to use the trained model to predict segmentation maps of unseen regions. Besides the notebook, we also provide supporting codes in a few packages within the repo. Some of them are useful for loading the workflow inputs, while others define model architecture and training hyperparameters. With that, I will shift to the notebook itself. For that, I will stop sharing and we'll resume sharing in a bit. You should probably be seeing my screen. Just let me know. Okay.
Yep, we can see it.
So before going through each of the notebooks, let me just show you what the crop segmentation folder looks like in a repo. And we have the 5 notebooks here in yellow, but also supporting code for the training and for different tasks of this, different steps of this task, including, for example, a code environment YAML file, an input region that we will train, and other codes as well. So we will start with the dataset generation notebook. So before running each of the notebooks, make sure that your code environment is set up with this requirement file that we provide, and that in this example that I'm running on the VS Code, make sure you selected the code environment. We are going to generate a data set for training the cropland segmentation task using a region that spans mostly 5,000 kilometers square over a period of 1 year. For the sake of time that we have here for the workshop, all the results are already run, and you will see how the outputs of the notebooks are already run as well. So you will see how the outputs of the cells in the training. So once the code environment is set up and we can start running, let's start with the dataset generation workflow. We start by importing some of the packages that we will need, and among them, we see our friend, as Renato said, get default vibe client, which instantiates the client and that communicates with the REST API. Besides those imports, I also define the workflow name that we run today, which is the data gen crop segmentation workflow, and also create a run name just to describe my execution. As I said, we are going to run this with an input region that is already provided to you in the repo. And for that, we will also generate a data set covering the whole year of 2020. So we reopen, we read the geometry and set up the time range, instantiate our clients. And as Renato said, we can always use this document workflow method from the client, passing as argument the workflow name to get a description of the workflow itself, both what the workflow does, but also the description of the sources, hints, parameters, and each of the tasks. Finally, for running this workflow, we are calling the run method, using as argument both the name of the workflow, the description that we defined it, and the geometry and time range as input parameters. This workflow run object has several properties that might be important. For example, the ID of the run, the status, and more important than the others, the output itself. For tracking the progress of a run, we can always call the monitor method from that run specifically, and we are going to see a list of the tasks with each of them has their own status, starting time, end time, and duration. As I previously run this workflow with the results already cached, you can see that the duration are mostly 0 seconds, so instant. But for this case, with these input region and geometry and time range, it is a process that takes several hours and requires several gigabytes of memory for generating this data set. But you can see that subsequent runs of these tasks, they are pretty much done instantly because we can fetch the results from the cache. If you look at the tasks here, as we see, there is the SpaceEye tasks, the CDL tasks, and the NDVI computation. But this matches the workflow definition that we saw on these slides. Finally, we can access the outputs of our workflow by accessing the output property of the run, indexing this dictionary with the sync names, which in this case are the CDL and the NDVI rasters. So this is the end for the data set generation notebook. We are going to visualize them in the second notebook and run a specifically custom workflow that also outputs intermediate rasters from this workflow so we can see them and explore them. So I'll move to the second notebook. Always before running, make sure that the code environment is selected and defined. In this example, we are going to import several of the packages that mostly, besides those that we already imported, are ones to print and to plot these images. We also defined several utility methods for either reading the assets or for plotting them. And then we are going to retrieve the results, the cached results from FarmVibes.AI platform in this new notebook. This is very similar to what we did in the first notebook, but it's just a more streamlined version for us to fetch the results more quickly. So in the end, what I'm doing is I am instantiating the client, defining the input geometry, time range, reading the input geometry, and then reading a custom workflow. We take a look on that in a while, and invoking a run with this custom workflow, and then checking the progress with it. So let's jump to the custom workflow and see the difference between this and the data generation one. So as we saw, the workflows are defined by a set of sources, sinks, parameters, and tasks. I've added this comment in green for each of the new things that I've added in comparison to the dataset generation workflow. And these are mostly 3 new sinks, which will be used for visualization. So we will have the rasters for the Sentinel-2 data, the cloud masks for the Sentinel-2 as well, and the SpaceEye rasters, which are the cloud-free images. And besides that, I added the task of the Sentinel-2 just to expose these sinks. The remainder of this workflow is just the same workflow that we ran previously. It has the CDL and the NDVI tasks, sinks, and the tasks as well. And it has the same edges, which is takes the cloud-free image and output and you feed that to the NDVI computation. So you can see that the progress looks very similar, but we now added the S2 tasks, which will output both the Sentinel-2 rasters and the cloud masks as well. We are going to recover the outputs of the workflow, accessing the output property and using the sink names as indexes for that. And here we see something interesting. The number of Sentinel-2 rasters that we are able to retrieve for that year of 2020 are 72 rasters. This is because of the 5-day cycle of Sentinel-2. As each raster is associated with a cloud and shadow mask, we also have 72 masks. However, SpaceEye is able to generate data daily, even though there is no Sentinel-2 raster associated with that date. And it does that by temporarily interpolating the data. For more details on that, you guys will see the SpaceEye session with Roberto Esteban. So we can see that SpaceEye outputs for us 366 rasters, and each raster, as they are NDVI is computed on top of those, we have the same number for NDVI as well. CDL, on the other hand, is just one map for the whole year. So the workflow will output just a single one for us. Okay, we finished running the workflow. Let's visualize the results. So we are selecting a few of them to show for you guys. And as a starting point, I will plot the Sentinel-2 raster. As you can see, this one for this specific date has a lot of clouds covering it. If we see the cloud mask that is associated with this raster, you can see that it covers most of the image. Finally, SpaceEye is able to recover that the regions with clouds that are obscured with cloud, and we can see that it is able to remove most of the clouds, but we do see some artifacts in the bottom corner. But it's way better than running a crop segmentation on top of the original image. Just to give a side-by-side comparison, we can see the Sentinel-2 image, the overlaid with the cloud mask, as well as the SpaceEye image. To get a better sense of the before and after for several dates, I'm also plotting here multiple Sentinel-2 images and their associated SpaceEye. As I said, more details will be on the following sessions. From the SpaceEye image, we also compute the NDVI, and here you can see that regions with cropland get a higher activations, which means higher values for NDVIs, and the river, for example, it gets a low activation for lower values. Finally, the CDL map. Here we show the map, and each color here is a different crop type. And we combine all the crop types to get to this binary crop map here. We do that by using a constant that we defined and is available as a support code for you, which we'll take a look. So these crop indices, they are the combined indices of all crop types in CDL, but we also provide some of the crop types for other types of crop indices for other crop of types, in a sense that if you want to specifically train this model for a different type of crop, you could by changing which crop type you are using. Okay, so that's it for the visualization notebook. Up until now, we were able to generate the data and visualize it, but let's see how we can train the model itself. So we are moving to the local training. I will go through it and then through the inference notebook, and then we will show how this can be done with AML. The idea is that both local training and AML training can be done interchangeably, and the inference will remain the same. So we start the notebook by defining and importing several of the packages that we'll need here. Besides those that we already imported, now we see several of imports for the PyTorch and PyTorch Lightning framework. We also import several of the supporting code that either take care of the crop data module, the PyTorch Lightning data module, or instantiating and defining the architecture of the model that we will train. We also define several training and dataset hyperparameters, which in this case are the size of the chip. Even though we are showing a region that is very big in terms of kilometers and image size, we are going to train our model with chips or patches of images of 256 by 256 pixels. And we'll show how this chip size will be used when instantiating the data module for us. We also define how many elements or chips compose on one epoch for us, the batch size, and the NDVI stack band. So these NDVI stack bands, as I show, we are temporarily sampling several NDVIs and stacking them in the channel dimension. In case you want to train this model with more or less of these bands, we are using 37 in this example. You could just alter here, and it will. What does it mean? It means that we are increasing or decreasing the gap in time between each band or in each NDVI band for us. And also we set some hyperparameters here for training, such as learning rate, weight k, and the number of epochs that we will train. As we did in the visualization notebook, this is mostly the same code for retrieving the results and the data set from the FarmVibes.AI. So defining the input geometry time range, instantiating the clients, and then running the dataset generation workflow with these parameters. We also monitor the progress, and you see this is exactly the same of the first notebook. And then we recover and save the outputs of our sinks to these two variables, CDL rasters and NDVI rasters. Now we're going to instantiate our data module. This is the PyTorch data module that will receive both the NDVI rasters and the CDL rasters and pre-process them for training. What it does for these two types of data is the NDVI, it will stack, it will first get all the rasters that we generated, compute the NDVI, and we'll temporarily sample then the number of bands that we define here as a parameter. For the CDL, it will get the CDL maps with all those crop indexes and then create the binary crop or non-crop map. Here, what it considers as positive indexes for the map, we are saying that we are going to use all the crop indices, but this could be changed for a specific crop if we want. And also we define the fall ratio in which we will split the input region into training and validation. I will show that in a few seconds. So with this code, we can instantiate the data module, and with setup, we can pre-process it, stacking the NDVIs and generating the binary crop map. For training and validation, we are going to split that input region that we had in two parts. The top 30%, which is the parameter defined by the raw ratio, is going to be our region that we will generate chips and patches for validation. And in this case, we will generate each patch here is 256 by 256, and we are sampling them in a grid manner throughout the region. On the training, on the other hand, we will sample random patches of the same size, 256 by 256, using the bottom 70% of the region. We also define the architecture and training hyperparameters using the segmentation model. We can also define the learning rates with ATK. We need to pass the number of channels that we selected, or the number of stack band, NDVI stack bands, and set up the training configuration. With that, we can either train our model, or in case we have already a model that was trained previously, we can just pass the checkpoint path for that and load it instead of training. Finally, we can validate the data, the model in the validation region, and measure some of the metrics such as accuracy, average precision, or the validation loss. Finally, we can export the trained model into a Nunes file. This is important because this will be used within the FarmVibes client platform to infer newer regions. So what we do here is we trace the model and set up to inference, and we define some of the shapes of the inputs and outputs expected by the model before exporting it with the Onyx library. After we export it, we can use the Onyx itself to check if the exported model works correctly. So this stops, the notebook stops here. We ended the training. Now we are going to go through the inference. We have the exported model. How do we do to infer a newer region? So we start the notebook by importing the previous packages. This is exactly the same that we did in the previous notebooks, instantiating the clients, defining an input region for the validation. Here, for the sake of the tutorial, we are going to use the same region as of the validation. So, but you could, if you want, define a different input region and a different input time range for testing the model. Here we trained, we read the validation, the input region, define the time range, and define the path of the model that we exported previously. With that, we run the FarmVibes.AI management script with that add Onyx command that Bruno showed us. It is able to include and to deploy the exported path that we defined back into the FarmVibes.AI Vibe cluster. Once that is run, we are good to go to infer new data. So for the inference itself, as I said, as I showed you in the slides, we have a inference node workflow. We can see informations about that workflow with the document workflow method from the client. And it will show us a description of the sources, the sinks, the workflow itself. And then we can run and invoke a run of this inference workflow. This time we are passing the geometry, the time range, and a new parameter here, which is the path of that, the name of that Onyx model that we deployed to the FarmVibes cluster. Running here, you can see that this workflow is very similar to the dataset generation, considering only the topmost flow, which was the download of Sentinel-2 data, the generation of cloud-free image with the SpaceEye, and then NDVI computation. After that, we have two workflows or two operations here that group the input raster, that stacks the input raster and run the inference in a parallel way. So you would stop probably here for the inference itself. You would be able to recover the output with accessing the output property and the dictionary associated with it. But for comparing both the predictions with the ground truth, we are going one step above, and we will get back that ground truth map that we used for validation. So what we do here is we retrieve the data set, the validation ground truth CDL mask for the validation region by retrieving that result from the cache. So just running the dataset generation again, recovering the CDL raster, and then getting the validation mask, binary mask here. So this is just the progress, which is done instantly because of the cache. And then we can plot both maps side by side here, or which the top is the predicted map for this validation region, and the bottom one is the ground truth binary map. So this would be the inference notebook. Let's see how the training can also be done with AML, but the inference itself would be the same. So we expect that once you get either training, you get to the exported model, we can perform the inference in a transparent way. So we are moving to the final notebook for today's tutorial. And for this one, we are going to show how the training can be integrated and leveraging the capabilities of Azure machine learning. So first and foremost, before running through it, make sure that you have your subscription, resource group, and workspace information defined here. In case you don't have one, make sure you make the account in Azure and set up the environment for running this notebook. We are going to import several of the packages that we had previously done in the older notebooks, define some of the parameters for dataset generation and training hyperparameters, and then define several important stuff for the AML example itself. So several of the packages that we will require for training, for interacting with the Azure ML for the AML environment, and defining several of the properties that we will be constants that we will use here. So let's go through each of them. We define several of the PEPs that will either store the data set or store the notebook, the model that we export back. We first and foremost, the Azure ML environment, we are going to set up a compute instance over there, which is a cluster of VMs that will run the training for us. So here we are defining just the name of this compute instance, can be any name that you want. And also what's the VM size. Here we are using a standard NC6, which is a VM with a single GPU. We also define the environment for running our experiment, which will involve, once the compute instance is set up, we'll raise a Docker container with a specific Docker image that we will see, and then install a series of packages that are defined by a Conda environment file here that we are we provide here in the repo. We are going, as we generated the data set with FarmVibes, we will need to transfer it to upload it to the AML environment. So here we define a set of the name, the version, and a description of this data set that will be uploaded. And also define the model information that we will need to register after it is trained. So by registering the model, we will make sure that it can be even reused by other folks within your subscription. Finally, we also define some of the hyperparameters for training, and as well as the number, for example, the number of GPUs that we will use during training, or the shared memory for that environment. As I said, we have run this code, which generates the data set for us, but the data will be local to the VM or the local AKS cluster that you are running. So what we want to do is we are going to generate a data set that is that will be used, that will be uploaded through an AML environment that we will use to train it. So what we do is, instead of uploading the whole raster, which will be huge, we are going to create the chips locally and then transfer that to the AML. So let's go through these steps. The first few steps here is just rerun the dataset generation, which will fetch the cached results for us, and recovering the CDL and the NDVI outputs. We are going to instantiate the same data module that we used for the local training. This will take care of pre-processing the NDVI's raster, stacking them channel-wise, and also generating the binary map for us. And so the big difference here is that besides defining the crop data module, we are calling the save chips locally for both the training and the validation sets. And this method, it will generate a series of chips of 256 by 256 and store it locally in a folder in this VM. Next, we are going to interact with AML to create our compute instance, upload the data set, and set up a job for training. So make sure that you are logged into Azure with the Azure login command. We are going to set up the ML client, which is the interface for us to communicate with the Azure machine learning environment. And this uses our subscription and resource group information. Once the client is set up, we can register a new data set and upload our data. So here we are passing as argument the AML dataset here, which is the path that we stored all the chips that we generated, and registering this in the AML environment as a new data asset. Finally, with our data uploaded, we can create a new compute instance. And this compute instance, in this case, will be an AML compute. And we set up the name of the compute that we defined earlier, the size of the VM. In this case, we are using the standard NC6 with one GPU, and other information about the how this compute instance will behave in case there are no jobs running, and so on and so forth. In case we already have a compute instance that is set up in Azure environment, this code will reuse it. Once the compute instance is online, we will need to set up an environment for running the training job. So this environment, it consists of a Docker container that we will use this one of the several images that Azure provides for this experiment, as well as one Conda environment path that we provide in the repo for with the packages that are required for running the training. Once that environment is set up as well, we can go to the job submission. Here, the job submission, we define the sets of inputs and the outputs. The set of inputs, mostly the path for the data set that we uploaded with the chips, and several of the parameters that we used in the local training, such as learning rates, weight decay, batch size, number of epochs. And here we can set up, for example, the number of GPUs. In this case, we are going to use one GPU. For the outputs, we are setting up a path to export the Onyx file. Then in the following steps, we're going to register that model and then downloading it back. But this just tells the job that there is an Onyx path that will be exported here. Finally, we are going to submit the job, and for that, we are going to run this AML training script. We are going to take a look at that in a while, but this command says that we are executing a Python script, which is this AML, with this set of inputs and outputs. And then we submitted the job with this command, and interact with their client to create this job and run. The job itself, Azure AML, it provides us as an endpoint to check the progress of the job and see how it is doing. And for example, checking the metrics and how the training is going on. So let's look at the AML training script just to see what we are doing behind the curtain. So the main book of the training script is very similar to what we did in the local training. We're going to set up a data module. This data module is slightly different than what we used in the local training, in the sense that it does not receive neither the NDVI rasters nor the CDL, but it receives a path to the directory that we generated and uploaded with the chips. So what it does is mostly loading the input NDVI stacks, the CDL map, the chips, and then providing a way to batch it and to output the data for the training model. We set up the segmentation model with the same hyperparameters that we used in the local training, and finally train the model. So this is mostly similar to what we did in the local. The thing is that Azure ML, besides using the GPUs and the capabilities of the environment, it allows us to log, for example, the metrics of the training. So we can use the ML flow package to log which are the metrics and even register the models. To register the Onyx, to export the Onyx model, we are doing the exactly same thing that we did in the local training. So tracing the model, defining the inputs and outputs shape, and then exporting with the Onyx package. And that's mostly the training script. We're going back to the notebook. Once the training is completed, we'll need to register the Onyx exported model. So we do that by defining a new model in the Azure environment, passing the path for that Onyx that we defined as an output of the job, and the name and the version of that model. This is useful in case other folks want to reuse this trained model in their own experiments within Azure ML, within ML, or download it and use it locally. Now that the model is registered in the environment, we can download it back by using the models pack, the download method, passing the name, the version, and where is the download path locally that we want to download it. And then this is an Onyx path that we interacted in the inference. So we can use Onyx to check if the model was exported correctly, but we can go through the inference notebook and add this, deploy this back to the FarmVibes.AI platform and use to infer a new region. And that's the end of the notebook. So throughout the tutorial today, we saw how to generate the data set for a region and a time range. We visualized several of the intermediate outputs of the dataset generation workflow. We saw how to train a crop segmentation model both locally or leveraging the AML capabilities, and also how to use this exported model to infer over newer regions. And that's all that I had today. The next tutorial will be from Alex, and we will see an example of weed detection with FarmVibes.AI. Thank you very much, and I'm glad to answer any questions in the chat.
My name is Alex Crown. I'm an engineer in Microsoft Research, and today with this presentation, I'm going to introduce you to the weed detection workflow in FarmVibes.AI. We'll start with a high-level overview of the workflow, the basic idea, and some of the key technologies that make it work. Next, I'll talk about raster images, how to make them, how to store them in Azure, and how to pass them to the workflow. Next, we'll go into detail about running the workflow, including setting optional parameters to fine-tune the results. Finally, I'll explain how to fetch the results and talk about a couple of options to analyze them. This is a high-level summary of the workflow. As with other workflows in FarmVibes.AI, the weed detection workflow requires a geometry and a time range to run. But this workflow also requires a remote raster image as input. Let's break that phrase down a bit. A raster image is just a two-dimensional grid of pixels, what you might be used to dealing with on your computer. JPEGs, PNGs, and TIFFs, they're all raster images. The weed detection workflow runs with TIFF files. Remote just means that the workflow expects the image to be accessible through the internet. You'll provide it a URL from which it can download the image. That doesn't mean that your images have to be publicly available. The URL can be signed such that the image is private, and only those with a specific key or token can access the file. I'll walk you through how to do that in just a bit. But once the inputs are gathered, the first thing the weed detection workflow does is download the raster. It then creates a Gaussian mixture model to cluster all the pixels in the input raster. At the high level, what we're telling the mixture model to do is bucket pixels into a predetermined number of buckets. Pixels with the same cluster are converted to polygons and written to shapefiles. The shapefiles generated by the workflow are helpful in identifying weeds in large fields. You can plug these into your precision sprayer, and instead of spraying entire fields, you can focus your attention and resources in areas flagged by the workflow. Now let's talk about how to create the appropriate images for this workflow. Drone imagery works best here. The low altitude, high resolution photos they take provide us with the right level of detail required to identify weeds or other anomalies. Running analysis over all the hundreds of photos that your drone takes, however, would be a painfully tedious process. So I'd like to highlight two options among many to convert the many photos that your drone takes into a single stitched image. Now, there are several companies that sell licenses to software that does just that. They'll stitch those images, hundreds of photos that your drone takes of your fields, and create a single orthomosaic image. Pix4D is one such company that comes to mind. At Microsoft, we're also working on a project called FarmVibes Edge. This will include Project Visage, a drone stitching algorithm that makes it easier to get interactive, low latency analytics. I've linked the research publication in the slide, and I'm happy to drop it in the chat after the talk. The interaction with Visage in FarmVibes Edge is simple. You take photos of your fields with your drone, and you then upload those photos to an edge device. You can do this through your local network or just by plugging in the SD card. That device will then run Visage, which will do the stitching for you, and it can be configured to automatically upload your stitched images to Azure when they're created. Now I'd like to spend some time talking about Azure storage. Azure is a safe place for you to store your drone imagery for long-term storage. Both file storage and blob storage are a great fit for drone imagery. File storage has directories and provides an intuitive way to organize your files, whereas blob storage is great for data that's written once and updated very rarely. That's generally the case with most drone images. Either way, it's hard to go wrong. You can securely share your stitched images from Azure with the weed detection workflow through signed URLs called Shared Access Signatures, or SAS tokens. These signatures allow you to share the data that you choose with fine-grained access control. I'd like to show you at least one way to create SAS tokens. Now you can use the Azure CLI or the Azure portal to do so, but my favorite way is to use the Microsoft Azure Storage Explorer application. Now in Azure Storage Explorer, you can log into your subscription or your storage account, or even the individual blob container or file share. You can navigate to the files that you want to share, and you can right-click on the file that you want to share, and the pop-up menu will give you the option to generate a shared access signature in the pop-up menu. You'll be prompted to select what permissions you want to grant the token and for how long the token is valid. The weed detection workflow only requires the read permission. So after you create this SAS token, copy the URL that's generated for you and pass that as input to the workflow. We'll get into how to do that in a bit. Now, as we discussed earlier, in order to work, the weed detection workflow requires a geometry, a time range, and a signed URL like a SAS token. Once you have those three items, you're good to go. On the right side of the slide, I'm showing an example raster and outlined a mock geometry to demonstrate what these inputs mean. The output of a weed detection workflow is a zip archive saved as a FarmVibes asset, as Renato mentioned, but I'm not going to get too deep into the implementation details. Just know that we can get access to this zip file without too much trouble. Now, this zip file called result.zip contains a shapefile and all the associated metadata files for each cluster of pixels identified in the image. On the screen, you see the output of a run generating 4 clusters. The input raster is displayed 5 times, once just by itself, and again with each of those individual buckets of pixels. You might notice that clusters don't overlap. Each pixel in the image belongs to only one cluster. In addition to the required inputs described before, we offer users a chance to provide optional parameters that can adjust the algorithm and fine-tune the results. You may want to explore some of these settings. No two fields are the same, and you may fly your drone at a particular altitude or use specific camera settings, or just have strict requirements for the output. We're confident that the default values will get you good results, but we give you the option to adjust these values and tailor the workflow to meet your needs. I'll walk through each of these one at a time. Now, as stated before, we use a Gaussian mixture model to cluster the pixels. To save time and space, we don't train the model with every pixel in the image. Rather, we randomly sample a subset of pixels when training the model. This value can be configured to any number of pixels. The current default is 100,000, but you can shift this up or down depending on your image size. The buffer is an offset from the edge of the input geometry that you specified in the workflow, and this is expressed in meters. This can help ensure that all pixels in the training set are containing useful data rather than empty space like you see in the corners of this raster. A negative value here will reduce the size of the geometry used for training, and a positive value will increase the size of the geometry. The red outline here indicates that we used a negative buffer in order to ensure that all of our pixels used for training were useful. Grid size is a tunable parameter for categorizing pixels into clusters during the prediction step. Each grid is sequentially loaded into memory, and each pixel within that grid is then assigned a cluster. This is done at the evaluation step, so changing this parameter does not affect the output, just the runtime of the workflow. Larger grids are generally faster until you reach the device's memory limit, so you probably don't need to mess with this parameter too much unless you know that your pods have an excess of memory. Clusters define the number of buckets into which pixels are classified. The default number of clusters is 4, as seen in the top right image. Below, we see the output from a 5-cluster run. You may want additional clusters if you have multiple crops within the same field or adjacent fields. At the same time, too many clusters may fragment your results and start to identify noise rather than useful signals. For our input data, 3 or 4 clusters has been about right. This is a parameter you should adjust based on your needs. Adjacent pixels of the same cluster are grouped together in polygons. You can see these little islands of this brown cluster and this yellow island within this larger brown cluster. Now, each cluster can have multiple polygons. Notice the brown and yellow islands in both images. Now, the sieve size determines the minimum size of one of these islands. If the size of this polygon is smaller than sieve size, it'll be sifted out and it'll be absorbed by its largest nearest neighbor. The image below has a much larger sieve size than the top image. Notice that this yellow island is completely removed, as are several of the brown islands. This is a useful tool for sifting out noise in your data, but you might want to be careful to not make it too large so you don't remove useful pieces of information. Simplify is an option for smoothing the borders of polygons. The two primary options are simplify and none. The top image has undergone simplification, and you can see that it has much smoother lines on the borders than the bottom image. Adding simplification to your polygons makes them easier to understand and consume less memory, and also makes them load faster in various applications that read shapefiles. Tolerance goes hand in hand with the simplify option. This parameter defines the maximum difference between the old polygon's points and the new polygon's edges. Any point closer than tolerance distance is deemed close enough and is liable to be removed. Now, both images here have been simplified, but the bottom image has undergone much more simplification. Note how much smoother the edges are in this bottom image, but also note how the polygons have shifted and moved. Now that we understand the inputs to the workflow, let's learn how to run it. There's a notebook in the FarmVibes.AI GitHub repo coming soon, which will help you get started with the weed detection workflow. You'll need to provide your own raster, which you know how to share with the SAS token, and you'll have to bring your own geometry that maps to that raster. I'm going to walk us through some key points from that notebook and explain what's going on. First, we'll need to install the dependencies required by Python. The easiest way to do this is to create a conda environment with the provided YAML file. Run these commands in your terminal to do so. From the project root, change directories into the weed detection notebook. Next, create the conda environment provided in the YAML. And finally, activate that environment. Next, we'll import our dependencies. We have our familiar Vibe core client, but we'll also import this external reference list, which we'll use on the next slide. For now, let's create our client and get going. Here, I've saved my SAS token as a URL, and I've saved the shape file for my field as this variable, boundary shape file. I'll use that variable and I'll read the file into memory, and I'll change the coordinate reference system to something that FarmVibes can understand, EPSG 4326. This gives us a data frame in the correct reference system. We'll then convert that data frame into a geometry with shapage. With shapely. We'll then create this external reference list using the time range for our flight, the geometry that we created, and the SAS token that we generated earlier. Now, there are two things I'd like to note here. First, for this time range, I'm using right now for the workflow. However, in a production environment, it would make a lot more sense to use the time that actually flew the drone as this time range. Second, the ID of this external reference list only relies on this SAS token. Due to the way that we cache data in FarmVibes, it makes a lot more sense to use the SAS token, the time range, and the geometry to develop this ID. Otherwise, we may not be able to update these later if we want to reuse our SAS token. Now that we have our external reference list and our client, we're ready to run the workflow. We call client run, and we provide the workflow name, which is FarmAI Agriculture Weed Detection. We'll give this instance a name, and we'll provide it that external reference list as our input data. With this, the weed detection workflow is now running in a pod in our FarmVibes instance. But what if I want to add and modify some of those parameters that we mentioned earlier? That's easy enough to do. All we need to do is create a dictionary where each parameter is named as a key, and its value is the value that we want to use for that parameter. And we'll pass that dictionary as the parameters argument in the workflow specification when we run it. Now, when you run a workflow, you immediately get returned a run object. Be sure to save this object. It has a lot of useful functions. But don't worry if you forget, you can always fetch it with the client. This run object is how you'll interact with the workflow. Now, we've seen this run monitor multiple times now in the previous presentations. It's useful for timing how long each op in your workflow takes to run. But there's a convenient side effect in that it pauses your Python workflow and script in order to wait for the workflow to complete before parsing the output. We take advantage of that here, and we parse the output. Now here I go through the details of pulling out the zip file from the data vibe dictionary returned by the workflow. But I'll save the implementation details for yourself to explore with the core data types defined on another screen. For now, the key idea here is that we have a path to the zip archive containing all of our shape files. What we can do with these is we can plot them in Python or download them to a local machine and use them however we'd like. There are two great ways to view the workflow output. GeoPandas, which provides a quick check in Python to see if the output is along the lines of what we expect, and QGIS, an open source application that lets us closely examine our geospatial data. Let's start with GeoPandas. There's some example code in the notebook that's coming soon that will get you started with displaying your shapefiles right in the notebook. You'll get to see each file layer on top of the input raster. Now, this is a great way to see if you're on the right track with your parameters. The downside of this solution is that you can't zoom in easily, and it makes it difficult to really understand what each cluster means and how each shape was generated. This is where QGIS comes in. If you download the workflow to a machine with QGIS installed, you can open each shapefile and inspect them with a high level of detail. I usually use SCP to download the results from my Azure machine to my local machine if I want to really understand the intricacies of my generated shapefiles. Here, you can see that I've zoomed in pretty far into the center of the image. And you can notice that it has identified this miscolored piece of crop. You can also layer the shapefiles together and see exactly where they board each other with complete lat-long coordinates. I hope this session has been helpful to anyone wishing to run the weed detection workflow, and I'm glad to field any questions in the chat. I believe we have a 5-minute break coming up. Thank you for your time.
Right. Hello, everyone. I'm Roberto Estevam, a research software engineer at Microsoft Research, and today I'll be presenting a demo on running SpaceEye in FarmVibes.AI. The objective of this demo is to showcase how to use FarmVibes.AI to generate daily cloud-free satellite imagery. SpaceEye is a neural network-based technique for clouding painting. The idea is to generate cloud-free multispectral imagery by fusing information from Sentinel-1 and Sentinel-2. Sentinel-2 carries a multispectral optical instrument, which is what we will reconstruct using SpaceEye. And Sentinel-1 satellites carry a SAR, synthetic aperture radar instrument, which is largely unaffected by weather conditions. The output is a raster that contains 10 of the 12 Sentinel-2 bands at 10-meter resolution. The model generates missing data by interpolation via temporal and spatial attention, which means it looks for similar patches in a spatial temporal window. Due to its temporal component, it is also able to generate predictions even if no imagery is available that day or if the image is completely covered by clouds. In FarmVibes.AI, the whole process for generating daily cloud-free images can be done by running the SpaceEye workflow. The workflow takes a region of interest and a time range as input and performs all the necessary data acquisition, pre-processing, and model inference in order to generate daily cloud-free imagery. This workflow can be divided into three main parts: Sentinel-2 pre-processing, Sentinel-1 pre-processing, and SpaceEye inference. The Sentinel-2 pre-processing workflow can be divided into roughly 5 steps. We first list all products that intersect with the input region and are inside the input time range. We then filter those products and keep a subset that is necessary to cover your input region. We download the data for each of the selected products and pre-process them by resampling all bands to 10-meter resolution and generating cloud masks from the product cloud geometries. And finally, we improve the product cloud masks by running machine learning models to segment clouds and cloud shadows and merge all three masks. The Sentinel-1 preprocessing workflow performs similar list and download operations to download Sentinel-1 data that intersects with the selected Sentinel-2 products. This data is then preprocessed by standard SAR preprocessing steps like the rank correction and also resampled to match the Sentinel-2 tiling grid. Finally, we merge all products that intersect with the same Sentinel-2 tile, and the output is Sentinel-1 data that is spatially aligned with Sentinel-2 imagery. On the SpaceEye inference workflow, we split the input data, which is Sentinel-2 imagery, cloud masks, and Sentinel-1 imagery, into spatial temporal chunks. We then perform inference for each chunk and merge the results at the end. This enables the user to specify time ranges and regions of interest that are larger than the model's inference window. So this is a short video that exemplifies the application of SpaceEye in monitoring crop fields. And you can see in the beginning the Sentinel-2 imagery, which is cloudy and not available every day. And then we can also see the RGB reconstructions of the data produced by SpaceEye. You can see that there is one image every day, and that it impinges the clouds. Moreover, the bands reconstructed by SpaceEye can be used to obtain many indices that are useful in crop monitoring. So this is an example of NDVI computed on top of SpaceEye predictions. And this is an example of NDWI computed on top of SpaceEye. So now I'm going to present a hands-on demo on how to run these workflows in your local FarmVibes.AI cluster using the Python client. Just going to share my screen with the Jupyter Notebook open and proceed with the hands-on demo. So before I begin, I just want to let you know that this notebook will be available in our GitHub page very soon. And you can access the GitHub page on github.com/Microsoft/FarmVibes.AI. You also have a link on the workshop page to the GitHub if you prefer to go that route. And if you're interested in running these examples in your own machine, you should be able to do so after setting up the cluster as discussed in the previous presentations. Please note that for a smoother demo and so we can fit this in our time constraints, I have already run all the workflows in this notebook. So when I request a workflow run, all the outputs will be fetched from my cluster cache. So if you run this by yourself, the actual compute time will be much longer. And I estimate it should take a few hours to run through all the workflows in this notebook. Another detail is that the workflows that process Sentinel-1 imagery require a Sci-Hub account. So please check the documentation on how to add secrets into your cluster in order to add the username and password for your Sci-Hub account so you can run the workflows that require or that process Sentinel-1 imagery. So let's begin by importing the necessary libraries and defining some helper functions, which are mostly used to help us visualize the data that we are working with. So I'm going to start by showcasing some Sentinel-2 data, right, on how you can use FarmVibes.AI to work with Sentinel-2 data. So let's begin by defining our workflow inputs, which are a region of interest and a time range. So on this, I'm defining the geometry here. This geometry is a shapely object defining EPSG for 326, which is also known as WGS84. So this is the longitude and this is the latitude. And I'm creating a box out of this point. And EPSG for 326 is the default coordinate system that we use for all metadata in FarmVibes.AI. This region right here is inside the Amazon rainforest in Brazil. And I'll show you where it is pretty soon. And as for our time range, I'm picking a 3-month period in 2018. So from the beginning of June up to the beginning of September. And if we look into where it is in relation to Brazil, this region of interest, we can see the Brazilian border in blue, the Amazon biome here shown in green, and this dot here represents our region of interest. Our actual region of interest is pretty small, so I'm just showing a dot to represent the centroid, and it's actually a square. But this is roughly where we're going to be looking at in the following examples. So let's begin by downloading Sentinel-2 data for that region and input time range. And to do that, we can use this data ingestion / Sentinel-2 / preprocess S2 workflows. So in general, these Sentinel-2 workflows will have this data ingestion Sentinel-2 prefix. So we first instantiate our Python client, And if you're interested in learning more about this workflow, you can always use the client's document workflow method, passing in the workflow name here. So if we run this, you can see there's a description for the workflow, the inputs and outputs, the parameters, and the tasks it will perform. So you can see these tasks, they roughly correspond to the tasks that I've shown in the slides. So to run the workflow, we can use the client's run method, and we pass in the name of the workflow we want to run. We can also pass in a run name, which is a user-defined name for this specific workflow run. Here I'm using Amazon and the year of this time range, so it's going to be Amazon 2018. Our input geometry, input time range, and optionally a few parameters that we want to run, right? We've seen before. And on this case, I'm passing this parameter here, PC key, which as discussed before is the Planetary Computer API key. This Planetary Computer API key is not required to run this workflow. So you could run this and download this anonymously without passing this parameter. But it is recommended that you do have a key if you plan on running several of these data ingestion workflows that interact with the Planetary Computer. You can request a key for free in the Planetary Computer website if you wish to do so. And you can see here that I have already registered this key as a secret in my local cluster, and I call that key pc-sub-key. And here's how you can use this add secret syntax to indicate that you want this parameter to be the resolution of this secret right here. So after we call this run, we can monitor as it runs. You can see that the tasks that were performed are roughly those tasks that I described in the PowerPoint slide. And you can see that in this case, the duration is basically 0, but that's because we are not rerunning anything. We are actually just fetching the results from cache, since I have already run this specific workflow before. So now that we have a run that is done, we can actually access the outputs using this output property of this run object right here. And we can see that this property will be a dictionary with the keys according to the sinks of this workflow. And in our case, we're mostly interested on this raster key, which is where we'll have the imagery from Sentinel-2. So just going to let this run while I speak. So we will have a reference to a TIFF file there that we downloaded, or several of them. But on the Sentinel-2 workflows, these outputs will be the entire Sentinel-2 tiles. And for reference, this Sentinel tiles are around 11,000 by 11,000 pixels at emitter resolution. So they're fairly large and usually larger than the input region you requested. But since these TIFFs are tiled, this means that we can actually read just a portion of the image we're interested in without having to load the whole file into memory. If you are interested in working with georeference rasters in Python and reading just parts of the image or the whole image or reading their metadata, I recommend learning about this raster.io library, which is what we're using throughout this demo to read metadata as well as image data from these georeference TIFF files. So before we read just a portion of the raster that resides inside our input geometry, we first need to project this geometry from our geographic coordinate system, right? So latitude and longitude, into the local projected coordinate system from the raster itself. So on this cell, what I'm doing is I'm getting this projected geometry into the raster coordinate system by reading the coordinate system using raster.io and then projecting the geometry using GeoPandas. And on this cell here, I plotted the whole tile with our region of interest highlighted in red here, just so you have an example of the size of the tile in relation to our region. But I also use this read raster function right here that is defined in the top of the notebook. And you can take a look at that if you're interested in it. And I'm just going to read the portion of the image that we're interested in without loading the whole file in the memory. And you can see this is the region or the imagery for the region that we are actually interested in. So this is the region that we'll be looking at for the remainder of this demo. So now that we know how to download Sentinel-2 data, I'm going to show you how to work with cloud masks. The workflow that we run before, which is the pre-process S2 workflow, did not run the machine learning models that I talked about before to produce higher quality cloud masks. So the pre-process S2 workflow is particularly useful if you don't plan on relying on cloud masks. For example, if you just want to manually inspect a set of images, I would recommend that workflow because you don't have to spend compute or wait for the machine learning models to run and improve your cloud mask. For other applications where cloud masks are desired, you can run this pre-process S2 improve mask workflow. And this workflow will actually perform all the tasks from the pre-process S2 workflow, as well as run the machine learning models in order to generate higher quality masks. So in the document workflow, you will also see the description for it. And in the tasks, you can see there is an S2 task here, which is actually the pre-process S2 workflow, which will download and pre-process the images, as well as this cloud task, which is a workflow that will improve the cloud masks. So we can use the same run method from the client using the same input geometry and time range, right? And we just need to change the name of the workflow we want to run, and I'm storing this on this variable run2. So as I run this workflow, again, you'll see the duration. Things are running really fast, but that's because I'm fetching results from the cache. But you can see these tasks right here are the same tasks as before. And we have new tasks here, which are running the cloud detection model, the cloud shadow detection model, and an operation that's merging all the masks. Now let's visualize the cloud masks overlaid on top of the image. Just to give an example of the difference in quality between the product cloud masks and our improved cloud masks that we obtained from the machine learning models. So I'm going to plot two columns here. On the left column, we have the image with the product mask overlaid on top of it. And on the right side, we have the same image, but we are overlaying the improved mask on top of it. And you can see the yellow regions are where the masks are signaling the cloudy regions. So you can see in these few examples that the improved mask is usually more accurate than the overlaid or the original product mask. So this is why we recommend running this workflow if you plan on relying on these cloud masks to do some kind of automatic processing. And in fact, this is the workflow that we use when we are running the SpaceEye workflow. The cloud mask can also be used, for example, to compute cloud cover just for the region of interest. So in this example, I'm going to compute the cloud cover for each of the products we have available for our region of interest, passing this projected polygon here. And I'm going to split the products that we have available into two sets. The first set I'm calling here is cloud-free rasters, and those are the sets, the images for which we have less than 10% cloud cover. And I have the other set, which I'm calling here cloudy rasters, which are the images for which we identify more than 10% cloud cover. So we can also check the cloud cover for each product with the associated capture date for that product. So you can see cloud cover can vary quite a bit. We have a few of the products with no cloud cover, some of them with very little cloud cover, and some of them with high or complete cloud cover as well. So now I'm going to plot the two sets of rasters that we created automatically. One where there is very little cloud cover, so the so-called cloud-free rasters, and you can see they're mostly cloud-free. A few of them have a little bit of cloud cover, but this does look like it respects our threshold of 10% cover. And these are the set of cloudy images. So you can see most of them are very heavily occluded by clouds and are above our 10% cloud cover threshold. So after this primer on how to work with Sentinel-2 images and cloud masks, let's run this workflow to visualize deforestation over a longer period of time in the same region of interest as before. So what I'm going to do now is I'm going to run the same workflow we did before. You can see I'm using the same workflow name. Here I'm calling Amazon plus the year of the workflow we're running. But here I'm running actually 5 times this client run, and I'm changing the time range. So I'm running the same 3-month period, but I'm running this 3-month period for 5 different years, right? From 2018 up to 2022. So we have images from this 3-month period for each of the years. And you can see we're running here. These runs are all running in parallel. So you can see it seems that this run is taking a bit longer, but that's because we're actually fetching the cache for all 5 of them at the same time. So after this is done, I'm going to plot a few of the images that we have available for each of the years. And the idea here is to just get a sense of what the images look like for each of the 3-month period in different years, right? So you can see after we run the first one and it is done, all the other ones are already marked as done because they were all actually running in parallel, right? So you can actually run multiple workflows in parallel in your cluster, either for the same type of workflow like we were doing here and with different inputs, or you can even run different workflows completely, right? And the orchestrator will take care of balancing the work and sharing the worker resources for all the workflows. So here's the available imagery over this 3-month period for each of the years. You can see each column is a different year. And depending on the day, we can have a little cloud cover or a very heavy cloud cover, right? So the reason I downloaded 3 months of data here is because since we're dealing with the Amazon rainforest, I was expecting there to be a lot of cloud cover. So I downloaded a larger portion so we could select some cloud-free images so you could compare and see through cloud-free images how deforestation was evolving in this region. So now I'm going to highlight, zoom in on a few selected images for each year, and we'll see what's happening in there. So for this specific example, I manually selected 1 image per year so you could see what it looked like. But you could, for example, using that cloud cover criteria that we've seen before, you could use some kind of automatic method of selection of images if you're interested in selecting a few good images in terms of cloud cover. So this is our reference image from 2018. And just to make it easier to see the effects of deforestation, I'm actually going to focus on this red subregion here on the top right of the image. So this is the that region right there, zoomed in. So let me zoom out on the notebook a little bit so we can see 2 of them at a time to see how it evolves. And you can see here from 2018 to 2019, the images look fairly similar. So there doesn't seem to be any meaningful change in terms of deforestation on this 1-year period. You can see it's not exactly 1 year apart because I selected an image that was cloud-free, right? So there's a little bit of wiggle room in there. And from 2019 to 2020, you can actually see this road that wasn't here before going to the forest, right? And there is a small deforested region right here that we couldn't see before. So this is already some early signs of deforestation happening in this area. If we go forward in time 1 year and look at 2021, you can see that the road goes deeper into the forest. And this deforested area here is much larger than in 2020. And if you go 1 year further still, so in 2022, this is relatively recent images, you can see that the road now goes deeper still into the forest. And besides this original deforested region that we've seen in 2021, you also see this region right here that wasn't deforested before. It's a fairly large region here without forest cover. So I just wanted to give you this example of how you could use FarmVibes.AI to get some insights using Sentinel-2 imagery, right? And you could notice that during all this notebook up to now, we've been kind of working around cloud cover, right? So now I'm going to go a bit forward, and we'll see how we can actually generate cloud-free images using SpaceEye. So as we discussed before, to generate SpaceEye images, we need Sentinel-1 data as well, right, besides Sentinel-2. So just to give you a quick idea of how we select Sentinel-1 products that should be downloaded for SpaceEye, I'm going to plot our input region here in red and the Sentinel-2 footprint products that we downloaded, which are shown here in green, and the Sentinel-1 product footprints here in blue. And you can see that we download all the data that we need to completely cover the Sentinel-2 footprint. So if we just want to pre-process data and have all the necessary Sentinel-1 and Sentinel-2 data available in order to run SpaceEye, we can run this data ingestion /SpaceEye /SpaceEye _preprocess. And you can see the documentation for it as well. And you can see that we have 3 sinks here, right? So the output of this workflow will be a list of Sentinel-2 rasters, which is what we had before, their respective cloud masks, right, as we had before as well. But we will also have Sentinel-1 rasters, right? And now that we run this, we can see the output keys. Now we have those same things that we were discussing. So S2 raster, S1 raster, and cloud mask. And I'm just going to plot the available data for both Sentinel-1 and Sentinel-2 in a small grid, so we can see the results. So this is the Sentinel-1 data that we have. So Sentinel-1 data is actually, we have it in forms of 2 bands, but here I'm making an RGB composite, so just so we can look at what it looks like, right? So this is a fairly standard RGB composite method for visualizing Sentinel-1 data. And here we have our Sentinel-2 data for that same time range, right? So one interesting thing is that Sentinel-1 originally is not in the same resolution or in the same grid as Sentinel-2, but we do some pre-processing to make sure that all the images are spatially aligned. So you can see the images have the same size. And you can also see that for Sentinel-2, we have varying amounts of cloud cover that will affect the images, like we've seen before. But for Sentinel-1, due to the SAR instrument, the images are basically unaffected by weather conditions. So this is the main motivation of trying to fuse Sentinel-1 and Sentinel-2 data in order to ink paint and kind of try to predict what was underneath the clouds. So here I'm just going to plot a close-up for 2 days where we had both Sentinel-1 and Sentinel-2 images. If we go back here, you can see that the dates for which we have images are different, and that's because we're getting images from different satellites, so they follow different orbits, and they will capture the same location at different days, right? So these are 2 captures that happened on the same day, and you can see that this day is relatively cloud-free, and this is the corresponding Sentinel-1 image. And you can see that this day is relatively cloud cover, but the clouds don't really affect the Sentinel-1 image. So now we're going to actually run the SpaceEye workflow to obtain cloud-free images, right? And running the SpaceEye workflow is just as easy as running all the other workflows. We just need to change the name to the SpaceEye workflow name, which is data underscore ingestion slash SpaceEye. And we're passing in the same geometry and same time range as before. And if we run this, this workflow actually calls the SpaceEye pre-process workflow inside of it. So you see there's this pre-process task where we're running all the Sentinel-2 pre-processing as well as all the Sentinel-1 pre-processing tasks. But we are also running the SpaceEye task right here, which is where we'll do the model inference to generate the in-painted versions of the images. So just to highlight that we generate daily imagery, I'm going to pick a 6-day interval. And here are the images for this 6-day interval as generated by SpaceEye. And here are the images from Sentinel-2. And you can see that for SpaceEye, we have one image available at each day. And for Sentinel-2, we have one image available on the first day, and then we have this 5-day revisit period until we have the next image available, right? So you can see these images here are black because we didn't have any, so I just plotted black boxes here. So SpaceEye can actually look through time and kind of interpolate what this sensor would see if it would pass over this region of the globe on that specific day. And now, just so we can take a closer look at the cloning painting capabilities of SpaceEye, I'm plotting the original Sentinel-2 image on the left and the SpaceEye reconstruction for that same day here on the right. So you can see for this example, where we have a relatively light cloud cover, SpaceEye is able to reconstruct the pixels that are obscured by clouds and cloud shadows as well. We have an example here with a bit more cloud cover, and you can see SpaceEye is still able to reconstruct it fairly well. And we also have examples where there is no cloud cover, and examples where we have complete cloud cover. And SpaceEye will use information from other captures, right, where there was information to reconstruct the image even at complete cloud cover. And as an extra information here, we also have a second SpaceEye method for generating cloud-free images, and it's also available as FarmVibes.AI, and is a method based on temporal depth interpolation. And this method doesn't use Sentinel-1 data, so it relies solely on cloud-free Sentinel-2 data to in-paint the cloudy pixels, and it can be accessed via this SpaceEye underscore interpolation workflow. And this is what we're going to do here. And for this example, I'm just going to run it on the 2020 the time range, just for some variety. And as we run this and monitor the workflow running, you can see that it does all the Sentinel-2 preprocessing steps, as well as the cloud improvements. But you see we don't download or pre-process Sentinel-1 data because this specific interpolation method does not rely on Sentinel-1. But we still have this SpaceEye task here, which will do the in-painting. And here are some examples of what that looks like. And yeah, this is an option in case your specific region doesn't have very good Sentinel-1 coverage, for example, or Sentinel-1 images aren't available for the period you're interested in for whatever reason. So you can try to use this as well. And you can see, for example, this image here, which is very heavily occluded by clouds, it is still able to reconstruct it and generate an image without the clouds. There are several other examples here. Again, this notebook with all the available images that I'm running live here will be available on GitHub. So if you have any questions, please feel free to ask them in the chat here. Or if you run into any trouble later on, you can also open an issue on GitHub to ask for support. So if you go into our GitHub page and on this issue tab right here, you can open a new issue to ask any questions for the team. And if you're using FarmVibes.AI for any of your products, you can also answer this issue right here, which was opened by us, to tell us what you're using SpaceEye or any other workflow for your application. So thank you everyone for your time. This is all I wanted to show for today, And next, Eduardo and Roberto will talk about sustainability practices and land degradation workflows.
Great. Thank you for staying with us to this section. We will be talking about land degradation and sustainability practices. So Roberto, Chandra, and me doing this segment to show some of the workflows we have in this sustainability to deal with sustainability issues, right? Right. So land degradation. So land degradation is an important issue, and it has been so that the United Nations has put forward this sustainability development goal specifically for this issue, so that we can halt and reverse this problem. And of course, in order to tackle the problem, we first need to identify where it's occurring, right? So we have to allocate the positions, the locations for the land degradation, and then we could apply some resources to tackle this problem, right? We will be using satellite images again for these identification, so that we can check what could be the causes of this. And I will be showing another data set related to weather to try to correlate the findings we are showing with that. We will be using again our friend NDVI. So again, as Rafael has mentioned before, we compute NDVI for have a sense of the vegetation that is in a certain place. But here we are using a different satellite, right? So in addition to Sentinel and a few other satellites, we have Landsat. The great benefit of Landsat is that we have images going back to 1982. So we are pulling these data sets from planetary computer and making that available on FarmVibes, so you can do this processing. And in this particular application, this is important because typically people look at long-term trends in NDVI to correlate that with the land degradation, right? So we have this a proxy that is linear trend of NDVI to correlate with the land degradation. If you see a negative trend in NDVI, that might be caused by land degradation. That's the point. But it's not enough to just look at the trends themselves to come to any conclusion, because as you know, climate change actually may operate and change rain patterns, right? So, and in FarmVibes, actually, we do have another data set that you can use to compute some statistics on precipitation. And actually, you can use that not only for these workflows, but you can also use to many other applications, right? So we have this CHIRPS data set that goes back to 1981, covering most of the globe in a resolution of 0.05 degrees. This is more or less 6 kilometers. So you can get this data. I'll show in a notebook in a few minutes. But yeah, you can use that in addition to compute trends, as I'm going to show here, also many other applications. Before going to the notebook, I want to mention one thing that's important that happens behind the scenes, right? Here we are going to show this, how to run the notebook for land degradation, but behind the scenes we have a couple of interesting things that you can use. I mean, you benefit from, and you can use to other workflows you might want to develop. This particular benefit here is these chunked computations. at the beginning of the presentation, Renato mentioned this fan in, fan out, that allows you to compute things in parallel, right? So if you imagine that you have many images to download, and you may spin up a cluster with many workers that would run those workers in parallel, so they will download the images. But in addition to that, you can do a bunch of other things in parallel. In particularly, this one is that you can compute some analysis over time in parallel. So the small little boxes you see here in this picture is just to convey that, right? So you may have many images and you want to compute something through time. In this case, it's just a linear trend, but soon you have other operators that will allow you to compute other time series in parallel over these chunks, right? And just to mention, in addition to parallelism, if you have many years, 20 years, let's say, of data that you want to load, I mean, since these images are very large, you probably want to check that up so it will not fill the memory and exhaust your memory, right? But let me switch to the notebook so you can see this example. By the way, these workflows, this notebook will be available in the GitHub repo, so you can run this yourself to see the results, right? And basically, I mean, this is pretty much similar to the other notebooks you have seen before. We import a bunch of utility libraries and get the full vibe client again. Same thing as before. And you specify region of interest you want to run. Again, same thing, no news here. And a time range. Specifically here, I'm running to a place in the Amazon because I want to show you some conclusions about that, but of course you are not limited to that. And also I have been running just 5 years here. Of course, as I mentioned, let's say you can go back way to 1982, for instance, and get probably a few days ago, the latest images. And you can get the full vibe clients as before, run the documentation flow. This happens to have just one single input, is the time range in geometry. In the end, you get, in addition to the linear trends I will show to you in a second, also the DVI. But of course, you can pick up other things, including the images themselves. PC key, if you have for planetary computer, if that's because we are downloading those images from Microsoft planetary computer, and then you run Landsat and trained over those, right? So this is what I'm doing here. By the way, the workflow is this one. I hope you can see clearly. And it will run a few things. One thing I want to mention on these is, again, it's runs behind the scene. You do not need to worry about check data, but it will check the data for you. And you may want to define some of the sizes of that small little boxes I was showing. But yeah, here I'm just using the default value. And once it runs, it returns a raster, right? So a raster with the trends for the vegetations. This is quite simply the linear trend over the signal of an DVI. If you pick many years, it will go up and down depending on the season, the region, right? But you can compute a trend, and that's basically what has been done to correlate with land degradation. If we open that up, I'm just opening reversorial here, you can see this result here. This is basically trends, right? So we have red for negative trend and blue for positive trend. So there is a river here. It's kind of a little bit hard because I didn't use a very low raster, but if you let me run here, there is a river over here. But yeah, you see that has been some negative trends in that region, right? So that might be correlated with land degradation. Well, you can ask, okay, so how about precipitation trends, right? Because that might explain things here. The reason for the decline in the vegetation or this application, the NDVI, might be related to the precipitation that's changing that area, right? For that, you have another workflow that is CHIRPS. As I mentioned, this is data set for precipitation in the resolution of more or less 6 kilometers. You have two frequencies, a daily one and monthly one. For this particular notebook, I have been using monthly frequencies. So I run these for the same period as before, the same 5 years from 2017 to 2021 to get this. And I return a set of images. In this case, it is a data set rather than a satellite image. But yeah, you can use again things like X-rays to open up it. And you can compute some trends as well. Here, I'm just doing in the notebook itself. You can, of course, do that other ways. And we can plot, again, the trend for this one. Here, I'm just plotting side by side, right? The image I had before and the trends for precipitation. And for the precipitation, actually, it seems that the trend is upward. So it doesn't seem to explain the decline in the NDVI signal. So unfortunately, I mean, I choose this specifically just to make a point of the types of analysis you can see. But here, I just want to finish the story with my slide. My last slide is just that this is deforestation, unfortunately. So you can see, you can pick the images, the landscape images for that region from 2017. Actually, it is the place here is close already to a city. It has been some deforestation over the years, but you can see that even in this period, 2017 to 2021, you can see an increase in the deforestation, right? So you can see the picture here on the right. It has kind of a pinkish color. This is deforestation. This is just a RGB image from Landsat. Well, this is what I had to show you. If you have any question on these workflows, any comment, please let me know. I will be looking at the chat. And now Roberto Santos will continue the presentation. Thank you so much.
Thanks, Eduardo. So this is the second part of the sustainability section, and I'm going to be talking a little bit about the workflow looking at sustainability practice. So we have a notebook that's going to be available soon at the Git repository, and it's part of a project that we have been running for a few months, where we are working alongside a partner to identify conservation practice at scale. So USDA has a long list of conservation practices that are desirable depending on your area, your environment, your weather. And we are tackling some of those conservation practices, in particular terraces. So what are terraces? Basically, terraces are an essential agricultural conservation practice. And it's labor intensive to identify those practices using remote sensing data. So the context of the project is we are not looking at variation over time, as we saw today on a few of the previous notebooks. We are looking at scale, geographic scale. Can we have a solution that can identify terraces over, let's say, whole state, using available data sets, remote sensing data, but also labels, and that's what we have done on this project. So this is one of the workflows that is available at FarmVibes.AI, and we are using the state-of-art land compact mapping and computer vision ML to address this question. So what is the high-level vision of this workflow? Basically, it's all about elevation. So we are looking at elevation and trying to identify the variation of this elevation across fields so that we can train a model to learn how to identify those terraces. So previously to this workflow, we had trained a model using basically DM data, so digital elevation model, and RGB data, so basically image that we can see, like the National Agriculture Imagery Program NAIP. So what we want to do is, from the DM data, we want to calculate the gradient so that we can see the variation in the elevation, and we are interested in understanding and looking at those where we can see like a very high variation on a short space of distance, and we are looking at also if this variation happens within the same class, the same land cover class. Why? Well, if we are looking at, for example, fields and rivers or fields and roads, you can expect to see some level of variation in the elevation between those two classes of land use. But if we see this variation within, let's say, a field, this could be a good hint for, okay, it might be a terrace that's happening here. So we use the DM for calculating the gradient, and then if you look at the bottom of this workflow, we have the overlap clustering operator. So basically, this overlap clustering is looking at the RGB and calculating local clusters. We are not really interested in understanding if the cluster that we see when we run the cluster on the top left pixel is the same one at the bottom right. We just want to understand that if this pixel follows in a class that's different from the pixels that are next to it. Okay, so once we have this cluster, we can calculate the average elevation per cluster. So we want to see what is the average elevation for this class, for this group in my cluster, let's say class group A, and let's do the same for the group B. And we assume that we're looking at different things. So if this variation is higher than we expect, we might have here another hint for the terraces. So basically, these are the two inputs that we use for training the model, and now this is the one that they are the ones that we use for running the inference on this workflow. So basically, DM gradient and average elevation per cluster. This is going to lead to an operator that calculates that through the inference of the machine learning. It's going to infer a result like the one on the right side. So we have the NAIP just to give us some special reference, but the output is basically a raster where each pixel in this raster has is defined as belongs to a particular class. Our current model, in fact, runs this for two conservation practices, terraces and grassy waterways. But for the purpose of this presentation, I'm going to just focus on the terraces. Okay, I'm going to just now go through some of the details in the data that we are looking at through this workflow. So basically, digital elevation model, we are using data sets that are available at the planetary computer. It varies in resolution across the US. but we can get good resolution at most part of the US. So once we get this DM, we can calculate the gradient, and as you can see, the gradient is basically just going to highlight areas where we have low or high variation in the elevation, and this is potentially visually, we could start like to get some, we could do some guesses about where we might have those terraces just by looking at the shape of these curves on the gradient. Okay, once we have this one, we can move to the NAPE. So basically, NAPE is a product that's available through USDA and is also available through Planetary Computer. We have the RGB IR bands. At the moment, we are just using the RGB for this for calculating the cluster. NAPE comes every more or less every 3 years for each state in the US. So basically, we try to pick a period that could match the labels that we had for this project, and then we run the overlap clustering. So the overlap clustering is basically, as I mentioned, is looking at for each pixel, it runs a cluster algorithm and look and try to place this pixel in one of 3 or 4 classes. That's basically the neighborhood. So we run the clustering around the neighborhood and we pick a particular class for this pixel. And we do this for each pixel in the image. As you can imagine, this is very time consuming and it consumes a lot of computational power because we have to run this for, let's say that we are talking about like a NAPE tile that's 7 kilometers per 5. This can take from a few minutes to hours, depending on how you define the parameters. So once you have the NAPE cluster, we can then move to the model. So we run these inputs through the inference, and you can see what we had before. So we have on the left side here NAPE without any results, any labels or model outputs. So we can visually identify some of those terraces as these curves that we can see on the image. If you have, it might be tricky to see at the first time if you're not familiar with the terraces, but if you look at the image in the middle of the slide, you can see the labels. So this is public available data run by the University of Iowa, where they are manually identifying those some practice over the state of Iowa. So we have used this data set to train our model. So you can see what we are taking as the ground truth for us. And on the right side, you can see the model output for this for this area. As you can see, we got a good amount of the areas that we can see on the labels. But just to give you a context, the aim here is not to try to replicate as much as possible the identification of the areas, but to get a sense of the existence of the terraces on those areas. So there is a post-processing stage where we overlap these images with the boundaries of the properties that we are interested in, and then we calculate the average number of the ratio between the number of pixels that are classed as terraces over the total number of pixels that are within that boundary, and this gives us the amount of pixels that we have on that a percentage of pixels on that boundary. And then we define a threshold that varies from area, and this is basically where the specialists come, the experts come and tell us, look, this amount, this particular threshold is enough to accept this as property with terraces or not. We have a notebook that's going to be available at the GitHub soon. I hope that you like this quick presentation about the sustainability practice. We are working on the conservation practices, working with partners to identify which ones are have more demand for more interest, and we're gonna have more news over the next week's months. Thank you very much. I'm gonna hand over to Ranveer now.
So with that, it has been a long session. Thank you everyone for joining. At this point, just wanted to say thank you to all the presenters. I think everyone did an awesome job. You heard a lot about everything we are doing, all the way from the vision of FarmVibes to how we are bringing everything to life through the work we are doing. I wanted to summarize again what are we doing at in the group around agriculture and food, and say where again all of this work fits in. So, we talked about how we want to make the entire food supply chain more data-driven, from capturing data from the farm to transferring the data to the supply chain to manufacturing the food itself. Today, you heard a lot about how we are getting data from the farm. It's part of it. There are other parts which Alex touched upon, was how do you get data from drones? There are other pieces of work on sensors, on communication that we haven't open sourced yet, but we will be making it available to the community. So the current focus areas for the group are, number one is on sustainability. So which is, you heard a lot about that today, on how do we estimate the emissions in a farm, to how do we adapt to climate change using things like microclimate prediction, to also doing things such as estimating the amount of carbon sequestered in soil, or figuring out what the sustainable practices are, like what Roberto mentioned. So that's one pillar of innovation in the group right now, is on sustainability. The other things that we are working on, the second one is on emerging markets. So there's work going on, some of it happening in our team in Africa, on how do you make digital agriculture more available to smallholder farmers worldwide. There's work we are doing with the World Bank, with the Gates Foundation and others, on making a lot of the tools that you heard of today and democratizing it, making it possible for smallholder farmers, where there are over 500 million smallholder farmers worldwide, and how do they benefit from all of these tools? So that's the second focus of the group, which we'll start talking more about over the next year. The third focus of the group is on the food supply chain. How do you capture information from the farm and transfer that data through the supply chain? People have talked a lot about blockchain, but the problem is not really blockchain. The bigger problem is, what do you put in the blockchain? How do you capture the information? How do you carry this information through the supply chain? You heard yesterday from Yuan on using DNA tags, that is carrying information in the DNA of material, but that's still an active research focus for the team on how do you make the food supply chain more transparent. There's work we are doing on building a knowledge graph as well for food. And the fourth key pillar for the group, which you heard a lot about yesterday, is what we are calling modern R&D. Essentially, it's for food production. How do you accelerate the innovation in food, leveraging genomics, leveraging chemistry, leveraging the phenotypes, and bringing all of the tech together, high performance compute, AI technologies, and so on. So this is the broad focus of the team. Today, you heard a lot about the FarmVibes.AI. Our goal with making these presentations was, one, to educate you, but second, to also hear from you and partner with you as we drive this change, this disruption in digital agriculture. So please do reach out if you have any thoughts, any insights, anything you think we are missing, or any way in which you could partner with us to take this to the farmers in different regions worldwide. So with that, I wanted to open it up to Q&A for and I see some of the questions here. We can start by answering them. I think you could also turn on your camera and answer if any of you have any questions.
Yeah, and also mic is enabled, so people can ask questions as well.
Yeah. So one question was, S, I don't know your full name. So your question was, what does using these tools in a commercial setting look like? So these are made available. So the work you saw today is made available through the MIT license. So you should be able to then leverage that license to make further additions, to even contribute back to the open source. And if you need to license any technology that we haven't made available, we have a licensing program at Microsoft through which we can license these technologies to you. And we do that with partners extensively. So, and yes, you also asked this question about what is the best way to work with the team. So we do have an alias, Riaz, if you could just point it here where you could send a note to us, ask any questions. We would love to. So the best way to work with us is if you're thinking about a particular impact could be either in terms of a new research that you're doing or a new partner or customer that needs the tools that we have built. And either you are the customer yourself or you are a partner where you hear this from a customer. The customer could be a food, an agriculture company, or it could be a non-profit organization, a governmental organization. If you see a need for these tools, please do reach out to us. So we have different ways in which we engage with partners to bring these capabilities to you. We'll support you depending on how we work with that particular customer to make sure that you're able to build the solution and take it to market. Hope that answered your question, yes. So there's Riaz and Jim on the call. Both of them work extensively with partners. So please, so they can also take your requests forward. Yeah, so Lokendra, you could send a mail on FarmVibes and we could take it from there, or Riaz can also directly connect you to the team. And in particular, if you could also add more details on the particular IP that you're interested in licensing, we can work with that as well.
Thanks.
Any other questions? I'm just reading here.
I think most questions were answered.
Yeah, Murat asked that question. I think Leo, you answered it. Yeah, so super resolution is there, nape imagery. And this is mostly about adding connectors for getting more data in. So if there's a particular data stream, say Planet Labs or anything else that you would like to add, you could add them yourself as well. We can provide you guidance, or over time, we will be adding more support too. Any other questions? Thank you so much, by the way, for attending, sitting through this entire long training session. Please do try things out. So we've made it, and we'd love to help you. If you run into roadblocks, if you run into any reason why you find it hard to use, please just send us a message. And we'll also make the entire recording available for people to use as well. You can listen to it. You can replay the recording, try things out as the different experts in the team were talking about it. Yeah, as Eduardo mentioned, PR and issues on GitHub are also a great way to interact, not just about code, but about features as well. Yeah, so thank you. And thanks, Yashwant. I think you're calling in from India. It's very late there. It's past 1 a.m. And thank you for staying up. And I know others are from different parts of the world. So Sumod, you asked a question. Do you have any updates on the release of the heat maps project? Yeah, so this is something we're actively working on, Sumod. We should have some updates on that. I won't release any timelines, but over the next year, you should definitely see. But if you have any priority customer on that, Sumod, please let us know. We'll prioritize. We have those components we built in-house. We need to make it more robust as we release it externally. So if you have any customer needs, to reach out to us and we'll try to expedite that.
Be the best contact for that specifically?
So Sumod, best would be to send it to FarmVibes, that email that Riaz mentioned. And then one of us will pick it up from there. We'll make sure to answer each of your questions. You have mine as well. And you could just send a note on GitHub as well. But FarmVibes, that email is the best one. We'll definitely respond.
That's perfect. Thank you so much.
Definitely. Thank you. Awesome. So if thanks, Priyanka. You have a farm network that uses these tools. Yeah, we have, if you want to see all of these in action, there is a farm in Eastern Washington, Andrew's farm. We can share the blog here as well, where we have the active use case. We always try the different technologies in his farm, but there are many other customers we work with too, which we haven't talked about publicly. Some of these, for example, we do with Land O'Lakes, and I'll be on stage next week at SVG Thrive with Land O'Lakes CTO, Teddy, talking about some of the broader work Microsoft is doing with Land O'Lakes. But in particular about all the research and how that is being used actively, you can read the blog that Riaz just posted in chat. So with that, thank you, everyone. I think anything else, Riaz or Jim, I think we are good. And please do reach out. We'd love to work with you.
Yeah, no, I think it's good. Thanks everyone for staying up and listening to the 4 hours of talk. I mean, we gave 15 minutes back, I guess.
Yeah, no, and 8 hours, going to be combining yesterday.
Yeah, 8 hours yesterday's and today. So
yeah, thank you. Thank you, everyone. Really looking forward to working with you. Thanks. Bye.
Bye.